So welcome to everybody. So in the name of the organizers and of ourselves, of course, we welcome you to CM3 session of the Marcel Grossman meeting 2021. So the first speaker will be Luca Mendola from Heidelberg. So please, Luca, you can start as you like.
Great, thanks a lot. So thanks a lot for giving me the opportunity of presenting this work. It's in collaboration with Miguel Quartin and also with Raul Abrama and Renan Boschetti, to different parts of this talk. All right, so it's very basic what I want to say essentially. So let's have a look at this well-known equation, the Friedmann-Robertson-Walker metric. And obviously, if you want to reconstruct the geometry of space-time, we would like to know this metric. And this means that we need to find A, or rather the increase, since we don't care about the absolute value, the increase of A, so H, A dot over A, and omega K. There are these two quantities. So the goal of finding the geometry of space-time reduces to the one of observing, measuring in some way H and omega K. Of course, I stay at the background. There could be a second part of my talk devoted to perturbations, but I will not have time to go into that. The question is, can we do this? Can we measure this H and this omega without assuming a cosmology? And as you will see, I will try to be precise with what I mean with this. But just to give a very obvious, simple idea, I will try to see whether it's possible to measure it without first saying I use lambda CDM or any other parameterization, neither a background, not a perturbation level, nor with other assumptions like concerning the bias, for instance, as you will see. All right, so I need to spend one slide on this idea of modeling dependency because it's a buzzword by now. Everybody's using this, so I want to be kind of specific what I mean with that. So sometimes you can see in the literature people call a technique model independent, meaning that you take a parameterization, but that is not based on a particular model, so on a particular cosmology. For instance, an expansion of H or Z in some mathematical series, not based on specific models. That could be an interesting approach, but it's not what I'm trying to do here. I really want to say something that is not based on any parameterization. You take the data, you manipulate the data, and you get a result which doesn't assume a particular cosmological model. Of course, you cannot be completely model independent. I don't think that exists. So I will assume various things. For instance, obviously, I will assume that standard candles exist, as you will see later on. I will assume that a Friedmann-Robertson-Walker metric, so homogeneity isotropy is a good approximation. So there will be several assumptions, but they're not related to the cosmological model, not to the one we call the cosmological models, which is a particular dark energy model or inflationary initial condition, these kind of things. So we aim at being independent of cosmology, specifically a background first order, and also independent of various other assumptions, as you will see, concerning, for instance, the bias. This is specifically and very precisely what I mean with model-independent approach. Let's go back to what we are saying. We need to find this quantity H, and H naught, I will not, although the topic of this session is H naught, I will not discuss H naught at all. I will discuss H of Z over H naught, so the expansion rate E, where E stands for expansion, but also perhaps for Einstein, and omega K. So we have these two quantities, and we want to measure them. As of course we know, standard candles give us a combination, which is this DL. You can see my pointer, right? It's the yellow Z, the luminosity distance. And this is a combination again of omega K and E. So if we know E of Z, then if we measure DL, of course, you can measure omega K. So there is a connection between these two quantities, but we still have to find a way to measure E of Z. At this point, you might say, well, but wait a moment, we know, everybody knows that omega K is 0, right? Well, maybe, maybe not. Omega K using only Planck data, CMB only, is actually slightly inconsistent with 0. And if you really just take Planck 2018 CMB only data, then you have strange results for H naught. So I would say the possibility that, and more importantly, all these numbers are based on lambda CDM plus curvature. So if you take a different model, you don't know exactly what you get, probably actually something different. So I assume that we actually don't know what omega K is. Okay, perhaps it's close to 0, we probably agree, but we don't know exactly what that is. So it's interesting to see where there is an independent way of measuring omega K. So my statement is to measure spatial curvature independently of the cosmological model. because we would like to know the geometry of our space-time, or particular space slices, independently of assumption or initial condition of cosmological model, we need to measure E of Z independently of the cosmological model. I think there is no way out of this kind of obvious but important statement. Of course, another obvious argument or objection could be, well, but we know how to measure H of Z because we can measure the BAO, the baryon acoustic oscillation, these famous wiggles. They are standard rulers. Indeed, you can take a standard ruler, put it in the sky, and measure the angular diameter distance, which is this quantity, which is also a combination of H and omega. It's actually the same combination we've seen earlier, except with some factor of 1 plus Z. And then you can take the same standard ruler, put along the line of sight, and then you measure this combination, the Z over R, which gives you H. So in some sense, you can say that putting a standard ruler with like BO, you can measure both H and omega K again. Yes, that's correct, but if you go a little bit deeper, then you realize that this is based on a number of assumptions. For instance, that the initial power spectrum, the transfer function, and the bias do not have intrinsic features. For instance, they don't have wiggles on their own. You might say, oh, that's very strange, contrived hypothesis that there is a bias with oscillations or initial power spectrum. Of course, if there are wiggles, that's very contrived, I will not support. But still, you're assuming a flat initial power spectrum. You assume featureless things. You assume a transfer function which just depends on K. So I would say that there is a number of assumptions even in the BO. And it's interesting to look for alternative ideas. All right, the alternative ideas is this. Standard candles give us DL, the luminosity distance, but also give us the scatter around Z. And if there is a scatter due to peculiar velocity, this red arrow, this will go on top of the cosmological redshift and will induce an extra delta Z and therefore an extra delta D. So, and this information can be used. So let's see how. The D, the luminosity distance, will be a function of the cosmological redshift plus the peculiar induced additional redshift due to the peculiar motion of supernovae. So I'm talking about standard candles, and from now on, I will always refer to supernovae, but the method is completely general. In fact, it's called clustering of standard candles. It can be applied to any standard candle, but just to fix it here, I will always mention, and we make forecasts for supernovae. So this can be written, of course, as a DL purely cosmological one, plus a correction, which is due to the peculiar velocity. Now we have to go through these three equations. If there is a peculiar velocity Vs, Hui and Green and other authors have shown that this will induce a change in the luminosity distance, which is given by this fractional change, which is again a function of the luminosity distance itself, or the derivative actually. But if there is a change in the luminosity distance, there is also a change in the magnitude, in the apparent magnitude, obviously because of the modulus distance equation. Therefore, there is a relation between what we want to know, the peculiar velocity, and what we see, a scatter in the magnitude of standard candles. If they're standard candles, they should have a magnitude. If there is a scatter, that's certainly due to various things, but one of these contributions will also be due to the peculiar velocity of the object itself. What is the scatter? What is the variance on this peculiar velocity? Well, of course, you can just take the equation and see that the scatter of the variance on the velocity field will be given by the intrinsic scatter of the supernovae, a conversion factor, the one we seen a moment ago, and on top of that, you can add a nonlinear scatter, because if you look at supernovae, they will also have their own peculiar velocity inside the galaxy, and that could be an extra factor, an extra contribution that you should take that into account as well. So we take all of them into account. Well, the next point, the next important point is that this linear, some part of the velocity field, the peculiar velocity field, the linear part, is actually correlated to the density contrast. It's not random. If you have an overdensity or underdensity, then in the linear regime, the object, the stars, the supernovae will fall, or the galaxy will fall into this overdensity or will go away from this underdensity. So there must be a relation between at least a component of the peculiar velocity field, the linear part, and the density contrast. This is well known, and this relation is given by this relation which appears in first order perturbation theory. The parallel component, the longitudinal component of the peculiar velocity is proportional to the density contrast of the galaxies times some factors, the most important of which is h. This mu is just the cosine angle, k is the wavelength, and z is other geometric things that we can measure, although I will make some comment about that, about the measurability of K and mu. But for now, let's focus only on the H and beta. So obviously, if we can measure V and if we can measure delta, and that's what we can do, we can measure V because of the scatter, we can measure delta because that's the power spectrum, then it means we can measure a combination of H and beta. Beta, by the way, is a well-known symbol that is used to identify the ratio of the growth to the bias in linear regime. It's F over B. So you say, well, you're not really much progress because now you have a combination of H and beta. How do you get H if you also have beta? Right, but beta, as we know, can also be measured by another thing, which is the Reshift distortion of the power spectrum. So all I'm saying, it's very simple, that if we have two random fields, peculiar velocity field V and delta density contrast, then we can build three correlation functions. And they, besides some overall factor we really not pay too much attention, can be written in this way. This is the standard power spectrum. This is the power spectrum of the peculiar velocity field. And this is the cross correlation between delta and V. And there is a bunch of symbols. There's also an extra smoothing that we insert in order to model the smoothing due to, for instance, if you have photometric uncertainties, or if there is the smoothing induced by a nonlinear peculiar velocity. So there are various components here, but all of them can be combined into this combination here, where you see there's a power spectrum, which is a factor for all three power spectra, just because there is a correlation between the peculiar velocity field, the linear part of the peculiar velocity field, and the power spectrum. So there is a P overall, and then there are various components. Now, in this bunch of symbols, there is again H here, there is also H squared there, and there is beta squared, but beta also appear independently on the power spectrum correlation function. So you see, at least in principle, intuitively, you see that there is a way to disentangle H and beta using these three quantities. All I say so far can be summarized in these slides. There is a likelihood, there are two random fields, delta and V. We assume them to be Gaussian random fields. There is a likelihood for these two random fields, and this likelihood is simply written as a Gaussian with some correlation matrix, covariance correlation matrix. And this correlation matrix can be written in this, using these symbols in this way. The only thing to note is that they're all proportional to P. In fact, I could have put P outside. Then there is some noise. I didn't mention on the noise part, but of course, there is a short noise term, which is just written in as 1 instead of 1 over n, just because I like to multiply everything by n. There's another short noise here, the one I showed earlier. There is no short noise on the cross correlation delta V. So these are the ingredients. There is a complication, however. The complication is that we don't have access to K and mu directly, to the cosine angle in K, but to K mu given a reference cosmology. For instance, you assume lambda CDM, you say, well, if lambda CDM is true, then I measure angles, I measure distances, and then I convert the redshift, I convert them using this reference cosmology. But we don't want to do that. So we need to generalize this. So if you take a generic reference cosmology, the relation for a generic cosmology of K mu is given by these two quantities. I think the first to write down this was Seyo and Eisenstein, and other people simply call them Alkop-Paczynski, although I think it should not really, it's not really, I would say from a more correct semantic point of view, should not be called Alkop-Paczynski, but some people just call it this way. And so there are these correction factors. However, they complicate the algebra, but not the substance, because this correction factor again depend on H and D, the luminosity distance, so the angular meter distance, and H, which are already factors in my equation. So they complicate the picture, but do not add an extra degree of complexity, because they do not add new degrees of freedom. So if you analyze these three observable, the three correlation functions, then you realize that they depend on these parameters. They depend on the luminosity or angular diameter distance combined with H naught. So I'm not discussing H naught at all. I take it for granted. So they, excuse me, they depend on, what is the pointer? They depend on the luminosity distance or angular diameter distance. They depend on E, the dimensionless expansion factor. They depend on beta, this bias and growth, which itself can depend arbitrarily on time and space. They depend on nonlinear velocity smoothing, which I didn't emphasize, but they are contained into the smoothing factor, sigma. They're just nuisance parameters. And they depend on the galaxy power spectrum, which is unknown and itself can depend arbitrarily on K and Z. So these 6 quantities, some of them only Z dependent, some of them K and Z dependent, completely specify the correlations at any linear k mu z, at any linear wavelength in particular, without assuming any cosmology. I'm not assuming a particular p. I say that p is a parameter on my equations. I not have to anywhere take a parameterization, neither lambda cm nor initial conditions. The same for beta. I say that all we observe from this point of view is contained into these 6 parameters. Actually, not 6 parameters, many more, because it's a 6 parameters for every z and every k. So it's a huge number of parameters, depend on how much you want to bin into k and z. But still, from some point of view, it's just 6 parameters. All right, well, the rest is actually forecast. So what you have to do now, and I will actually be kind of quick, and I realize that I will be very quick, so we can save some minutes for the next speakers. Because you see, there's not much point now in going into too many details, because all I have to do is to take my likelihood here.
So you have 3 minutes, yeah.
Okay, good. So I use them and make the Fisher matrix and take an ideal experiment. We take LST at the Vero Rabin Observatory, take the specification of LST, and as usual in these cases, you make a pessimistic, an optimistic, and then you might change this or that. So there are many details, of course, that I invite you to read if you're interested in our papers. But the overall idea is that using this, you can produce the estimate of the error on H, marginalizing over all the other parameters without assuming any behavioral bias for cosmology, initial conditions, whatever, because they're being factorized into different parameters. Of course, you can put constraints also on the other parameters, but I'm focusing only on H. You can get constraints on beta, on P, but that's not what is particularly interesting for me at this moment. And then we found that you can measure delta H over H to 6 or even 5% using LST, a bit optimistic on the optimistic side, with sort of 100,000s up to 1 million supernovae 1A. So that could be perhaps slightly optimistic now, but that is what LST could promise, could achieve, or actually even pass it. And there are various ways to improve it, like combining with other experiments, but I'll not discuss that because I just want to present the idea. So the idea is that indeed you can get this constraint to 5%, even a Reshift like 0.5, 0.6. There's this busy plot in which you can see delta H over H as a function of the density of supernovae per cubic megaparsec. And this is the plots that we can put at various Reshift. Or even better, you simply compactify all the information in this simple formula, which gives you the error on delta H over H of the order of 6% times factors that depends on the number of supernovae, the Reshift at which you are, and the sigma intrinsic that we take to be 0.13 as prescribed by the experiments. Well, I'm done. I just read this. The conclusions are, models are good, but we need to be aware of limitations and assumptions. It's really important to spell them out and see whether the answer we give to our question do or do not, or how much they depend on the assumed model. For instance, is the result the space curvature is 0 a model independent statement? Certainly is not. Is W equal to -1 a model dependent statement? Certainly is not. Is modified gravity eta parameter equal 0, not 0, model independent statement? Yes, if you use the right method. No, if you use another method. So I will not have time to discuss that. But what I want to say is that, of course, making models is very good. We do models all the time. But in some cases, you can do cosmology without assuming a cosmology. So if there are those cases, I think we should use this possibility. And in particular, I've shown that you can measure Hz over H0 down to a few percent without cosmological assumptions with this method, which is called clustering of standard candles. Thanks a lot for listening.
Thank you very much, Luca. Just in time, very good.
Very good.
So, so if there is any question, I invite to pose these questions, please.
Everybody's happy.
It seems that everybody's happy, yeah.
Maybe I can ask a question, Luca.
Sure.
I'm wondering about what I'm going to talk about is interacting models it looks like there's an assumption that indeed the growth of structure is simply related to the velocity infall.
Continuity, yes.
Yes, yeah.
Indeed.
So I guess, which is most would consider a reasonable assumption, I guess. But I guess that is one way to break your model, break your model independence.
Very good point. Absolutely, I like this. I thought about that, David, also because I remember some interaction we had some years ago on vacuum models, and indeed, I expect this to be the case. I'm actually curious to see what happens in that case and whether one can recover model dependency in some way. I don't have a complete answer. I agree completely with you. I assume continuity, and that is a crucial assumption. And I'm at, of course, a sub-horizon scale. So typically when you have a change there, then it's a large scale. So it might be that this just saves the problem. But if you really insist on violating that at the scales we are observing, then I guess something else should be done. And it's an interesting question. I don't know. I'm aware of this problem. Thank you for pointing that out. And I don't have a general solution. That should be, I guess, seen case by case, what you can do about it. Thanks.
Okay, we can still have a question by Joseph Kurubila, please.
Yeah, very nice talk, Luca. I had a question regarding your modeling here for P of K, for example. How far can you push this model? Because this is linear.
Again, how can you?
How far for K max can you push this?
Okay. Of course, that's an important question. So in our paper, we use 0.1 because we try to be linear.
Mm-hmm.
You see, P of K, I don't have to model it. So P of K is one parameter, and you can give me any P of K. Oh, by the way, of course, I did forecast, and doing forecast, I had to make a fiducial model, but it's not breaking the model dependency. So when I have data, of course, data will replace the fiducial model, but that's not the important point. The important point is that P of K are not taking, so I'm not assuming a linear for the fiducial, yes, but otherwise I don't think I need to assume a linear or a particular P of K. If I take the data, I can use the data themselves. However, all the other steps in the calculations, including the Kaiser distortion and the linear relation of continuity, is based on linear physics, absolutely. So you need to stick some level like 0.1 or something, or check whether. So we extended a bit, 0.2, 0.3, just for fun to see what happens. Of course, you improve a little bit the constraints, but all the numbers I quoted are to Kmax equal to 0.1, which otherwise is pretty conservative because in the past it was actually a bit better than this. So we took 0.1, which is a good value today, and it's better the more you go into the past, but we try to be slightly conservative. It's a good point. Thanks a lot.
Okay, thank you. I think we can just move to the next talk. Thanks. By David Wands on interacting vacuum cosmology and observational constraints. So please, David.
Okay, thank you. I hope you can see my screen.
Yes.
Just put that in full screen.
It is fine.
Okay, so thanks very much to the organizers for the chance to present my work here. I'm going to talk about a particular kind of class of cosmological models, interacting vacuum models, and I'll say a bit about the observational constraints on these. I have a paper in preparation with Chakrit, Husha, and Yasha in Portsmouth. I realize in discussing the models, I'll talk about work done with a number of people over recent years who have also listed here. For this audience, for this session, I won't spend too much time motivating the study of dark energy cosmologies. We all know that the majority of the energy density in our universe today is in the form of some kind of dark energy. And indeed, much of the rest is in dark matter. And there are, of course, many different approaches to parameterizing or describing that dark energy. And I should say I'll do this in the context of dark energy components in general relativity. So certainly the starting point would be a cosmological constant, which is a vacuum cosmology where the vacuum energy is a constant. The equation of state is fixed. Pressure is equal to minus the energy density. And there's no energy transfer to or from that vacuum. So we really have a cosmological constant. But there's much interest in seeing whether observations probe some different kind of model of dark energy. And often the first starting point is to consider varying the equation of state away from -1. And that, of course, gives rise to a time or redshift dependent dark energy density. And indeed, beyond that, one can go on and look at models of dark energy where there's also energy transfer between, in particular, I'll be thinking about models here where the energy transfer is between dark energy and the dark matter, these two components in the dark sector. But I'm going to step back from looking at models where you vary both the equation of state and the energy transfer. I'm going to focus just on a maybe simple class of models where we can study the energy transfer, but fix the equation of state. So these really are vacuum models where the pressure is equal to minus the density, but nonetheless, an energy transfer can lead to time and redshift dependent vacuum energy density. And I think that's interesting because we can test these ideas through cosmological observations. And in particular, I'll say a little bit about how it might offer an interesting perspective on some of the tensions in the cosmological data, if indeed we had just a non-interacting vacuum. So I think it's, let me define the model that I'm going to be studying, describing here. The starting point is, as I say, this is just the energy of the vacuum. So it's undiluted by the expansion of the universe. We're not introducing any new degrees of freedom in the model. And my real definition is that it's an energy momentum tensor that's just proportional to the metric. And that constant of proportionality is the vacuum energy. And of course, that's a special case of a perfect fluid where, as I was saying, we fix the equation of state. So if the pressure is equal to minus the density, we're left with the energy momentum tensor proportional to the metric. And of course, a consequence of that is that there's no velocity, there's no preferred fall velocity associated with the vacuum because, of course, there's no particle flow. But equally, you can define the vacuum, therefore, by saying that at any given space-time point, every observer sees, with whatever their fall velocity, sees the energy density of the vacuum to be V. Okay, so there's no velocity, there's no momentum of the vacuum. But once we start allowing for an energy momentum transfer, there can be, there is a direction associated with that energy momentum flow. So I'm going to use the full vector Q to describe the energy momentum transfer to the vacuum. So the non-conservation of the energy momentum tensor, the divergence of the energy momentum tensor is given by Q. And for the vacuum, that's just the gradient of the vacuum energy V. But working in general relativity, I've got to conserve the total energy momentum tensor. So I'll be considering that energy momentum transfer must come from the matter, so specifically the dark matter. And then we see lambda CDM as just a special case of that, in which we set the energy momentum transfer to 0. So, of course, this has been studied over many years in terms of the evolution of the background cosmology, considering the possibility of a time-dependent vacuum energy. Of course, in a homogeneous and isotropic cosmology, that energy flow is then just a purely time-like energy flow. So instead of a full vector Q, we can just describe it by a scalar energy transfer Q. And so in my notation, Q is just determines the time dependence of the vacuum V dot. And the other flip side to that is it has to come from the matter. So you modify the continuity equation for matter. And different models have been discussed and described where Q can be written in terms of the expansion of the universe and the energy densities in the universe. And typically, simple models, you just can then use a single dimensionless parameter alpha or Q to describe that energy transfer. So I'm going to be talking mainly here about the first example here where the energy transfer is proportional to the matter density with a dimensionless coefficient alpha. So I'll call that decaying dark matter model, but it's also one a realization the phenomenology is the same as the running vacuum model described by our chair and his collaborators and other researchers. As I say, there are other models, decaying vacuum energy models, or models that reproduce the dynamics of some unified dark matter models, like the Chakrajan gas model, have been studied in this way. And the concern might be that, of course, we can then describe any background evolution by a suitable specification of the vacuum energy. So perhaps we're not really explaining anything. And so I think that's why I'm interested in studying the cosmological perturbations in these models. It's really a way to explore the physics, the physical description of the models. So I'd like to just look at, give you a crash course in the dynamics, the fluid mechanics of the vacuum. You can look at basic principles like energy conservation and momentum conservation once we include the perturbations. So this energy flow now, as well as perturbing the energy transfer Q, we should in general include a momentum transfer F, or a force acting on the vacuum. So the perturbation in the rate of change of the vacuum energy is determined by the perturbation in the energy transfer. That's the energy conservation equation. But there's also a sort of momentum conservation equation for the vacuum. Now the vacuum has no momentum, but it has a pressure. And so if you have an inhomogeneous vacuum, there's a pressure gradient, and that has to be balanced by the force exerted on the vacuum by the matter to maintain zero momentum. So you get this sort of nice result that the force is balanced by the pressure gradient. And then using Newtonian mechanics of the vacuum, it applies to the vacuum as well. So just as the matter exerts a force on the vacuum, so the vacuum exerts this force F, an equal and opposite force back on the matter, and that enters into the evolution of the matter perturbations. What I will, in the rest of this talk, and indeed in most of the phenomenological studies, are focused on the simplest case phenomenologically, where the energy transfer, the energy momentum flow is along the 4 vector of the matter. Because in that case, there's no momentum transfer, there's no force acting on the matter in its co-moving frame. And from this equation, you can see that means that there's no vacuum perturbation in that co-moving gauge. And so if the matter has no force acting on it, it's free falling. It follows geodesics, just as we expect cold dark matter to do. So that's as much as I really to say about the theory. If I move on just to talking about then some of the phenomenology of this we see, and this is focusing on this decaying dark matter model. Of course, the observational constraints, certainly in terms of the matter content of the early universe, the primary constraints come from the cosmic microwave background. And if we apply the constraints from the Planck temperature and polarization spectra, then the acoustic peaks really constrain the matter density at the time of last scattering, or the radiation to matter ratio at the time of last scattering. And now in an interacting model, of course, there's a difference between having fixed the matter density at the time of last scattering, we still have a freedom in the matter density at the present day according to what the energy transfer to or from the dark matter is. So with my notations, if we have a positive Q, then there'll be any energy transfer to the vacuum, decreasing the matter density after last scattering. So we see a degeneracy here in the contour plot for the present dark matter energy density, a degeneracy between that and the value of alpha, which was my dimensionless parameterization of the coupling Q. So we have degeneracy between alpha and the whole dark matter density, but we'll also, that leads to other degeneracies. And in particular, changing the dark matter density, in particular, we think of decreasing the dark matter density at late times. Well, that's increasing the redshift of matter dark energy equality, which can increase the horizon size to maintain the fixed horizon size to the last scattering surface. Actually, we have to then increase H0. So again, increasing the Hubble constant, decreasing the Hubble length. So we see a degeneracy between alpha and H0. And as we'll also see, increasing alpha also increases the growth rate of the matter perturbations, which will increase sigma 8, the amplitude of the matter power spectrum. So just to present the effect of that on some of the key parameters in the model, here's likelihood plots for alpha against the Hubble constant and against sigma 8. The gray contours are just from the Planck data, just from CMB data. And this introduction of a coupling between the dark matter and the vacuum gives a large degeneracy between alpha and H0, large in the sense that H0 can vary between 50 and 80 almost, and still be compatible with the CMB data. So this at face value gives you the opportunity to resolve tensions between CMB estimations of H0 and high values, or indeed, or it could be very low values of H0 from low redshift observations. If we put in some constraints like the cosmic clocks, constraints on the age of galaxies, so constraining h of z at low redshift, cosmic clocks is a fairly mild constraint on the Hubble parameter, then that begins to cut off very, very low values of H0, very large, very negative values of alpha. And if we continue and actually add in measurements of the galaxy power spectrum, the baryon acoustic oscillations, which constrain h of z much more tightly at low redshift, then we get back to a very tight constraint on alpha, which is consistent with 0 here, plus or minus about 0.001.
3 minutes, David. 3.
Thank you. And that also constrains, and then we're back to a much more familiar looking constraint on H0. So if I put those numbers in, then we have a much more familiar looking constraint on H0 of about 68 plus or minus 1. So in this, and I should say what I'm presenting here is I was hoping when I submitted the talk to have public results out and available, but this is preliminary results still as yet. But just by combining these data sets in this simple model, we see really there is a potential degeneracy between alpha and H0, but the constraints, applying this data, we really find we're close back to the lambda CDM model. We've simply allowed a larger, there is a larger variation allowed in H0 than in a more constrained lambda CDM model. And that offers the possibility perhaps of easing tensions, but we're not claiming to have solved that. And in particular, the other feature you tend to see in these models that is, if you allow for a large H0, then that also increases sigma 8, only slightly, but large H0 would again tend to be associated with a larger tension in the values of sigma 8 favored by the CMB compared with other large scale structure surveys. So if I should just mention, I probably don't have time to go through this unless anyone has questions, but one does have to be careful in using data such as redshift space distortions in these models. precisely because of this effect I was just mentioning to Luca, the fact that in non-interacting models, we can associate the growth of structure entirely with the infall of matter, and that's reflected in redshift space distortions in the galaxy power spectrum. For interacting matter, it's really necessary to include the effect of the interaction terms, and that modifies the relation between the redshift space distortions and F sigma 8. So I should conclude almost just about in time.
You're in time, don't worry.
Probably not, maybe not time to go through all these points. Rather than listing conclusions, I was just going to list lots of outstanding challenges. There's lots, I think, even in a relatively simple idea like this, there's lots of details we don't understand. I haven't talked about a microphysical model of the where the energy exchange with the vacuum comes from. And that's obviously an interesting question. I really focused on the phenomenology. Even within the phenomenology, most of the studies pick specific models of the interaction. And of course, it's very interesting to think whether we can make model independent conclusions or tests of the idea, and work on that has begun. I've quoted some of the references here, which either look at switching, introducing periods where the interaction can switch on and off, or indeed trying to allow do a sort of multiple principal component analysis of that variation. But what we can say so far, I think what we see is the general lessons seem to be that there is a potential degeneracy between the interaction strength and the Hubble constant. This can at least ease some of the tensions of the CMB with high values of H0 measured at low redshift, but increasing H0 tends to increase sigma 8. At which point I should probably a good point to stop and see if we have time for any questions. Thank you.
Okay, thank you very much, David. So is there any question to this talk? You can raise hands or... No question? Everything...
Can I ask a quick question, John? Sorry,
yes.
I didn't raise my hand.
Okay.
This effect you mentioned, the Reshift distortion, how big that is? Can you quantify? Can you say something more quantitative?
It's well, in fact, yeah. So the term you find in these models is as given here. It's sort of the energy transfer relative to the matter density. So that's actually alpha H in this particular model, for example. So I probably at this point I should have this should be a schematic equals here. I think I'm missing a factor of H squared. So I think basically the correction is of order alpha to F. And if you remember, alpha is constrained to be about 0.1. So, well, no, sorry, alpha is constrained to be much smaller than 0.1. So I guess that's quite a small correction to F. Yeah, which is of order 1. So of course, F is usually 1 in the matter-dominated era, for example, and then gets smaller as dark energy dominates, but still is, I guess, of order 1 today. You might have a number off the top of your head, but yeah. So I guess if alpha's really down at the 10 to the minus 2, 10 to the minus 3 level, it's really quite then becoming a subdominant effect. Yeah. So it wouldn't be necessarily a problem in your model. The other thing was just that actually this is an example where that effect is still this interaction in these geodesic models where for the energy transfer, this term is always actually proportional to the density contrast. So it would be like a small change perhaps in the bias effect rather than breaking the relationship you were looking at in your model, I think.
If it can be absorbed in the bias, then probably will not change.
Yeah.
Thanks.
Okay, thank you. I just want to comment that the kind of results you have shown on sigma 8 and 8.0, they are essentially compatible with what we have obtained recently. But of course, yeah, it's difficult to get sigma 8 low, 8's not high. What we have done is to admit the possibility that G can change, I mean, gravitational coupling can change mildly, logarithmically, okay? And in doing this, then we can harmonize better this possibility to have the two tensions under control, okay? But if you don't do this, then of course, what you find is what you have shown, that 8.0 remains low and sigma 8 relatively high, or at least it's not possible to solve the two tensions at a time. So by introducing this change of G into this game, it can be improved. Just a comment, okay? I don't want to make
Yeah,
it
that's right.
lengthier.
Obviously, it's constraining once you fix a form for that energy transfer, and so it's interesting to think about what flexibility there is, what's essential.
What we do is to avoid the interaction between vacuum and matter. There is no interaction, and what we have is then an evolution of a mild evolution of the cosmology of the gravitational constant.
Yeah, that's right. So,
of course, you can have everything all together, but we did not study this possibility yet because it is actually not analytical too. Yeah. Okay, thank you very much, David. So we have to move on. So I am calling Eleonora. Okay, Eleonora is here. Very good. So please, is your turn. You can start as soon as you like.
Right?
Yes, we can see. Good.
Thank you.
So
okay,
please go on.
Thanks a lot. Thanks a lot for the invitation to talk.
Thank you for coming.
Okay, so let's start with the standard model. The standard model that we now assume in cosmology is the Lambda matter model, because this can provide a remarkable fit of a wide range of cosmological and astrophysical data. However, this is based on known quantities, and the physical evidence can just from cosmological and astrophysical observations without a strong theoretical motivation. These three unknown pillars are the inflation, the dark matter, and the dark energy. And in the standard model, we are choosing the most simplest form for these quantities. So we have the inflation that is given by a single minimally coupled zero-Rayleigh scalar field, the dark matter that is a pressureless fluid, maybe called the collisionless particles, and the dark energy that is a cosmological constant term. So the 6-parameter approach lacks the deep underpinnings a model requires to approach fundamental physics law, and is more similar to an effective theory of an underlying physical theory yet to be discovered. For this reason, with the increase of the experimental sensitivity, deviations from this model are expected, and in this context, the discrepancies among the key cosmological parameters we see in the data, if are not due to systematics, can be due to a failure of the model assumed to analyze the data. The most statistically significant, long-lasting, and widely persisting tension is the Hubble constant disagreement between the value estimated by Planck, assuming a lambda dark matter model, and the value measured by the Schu's collaboration using supernovae calibrated with C-phase. However, we don't have just these two measurements. We have other CMB ground-based telescope measurements like SPT3G and ACT data release 4, and both of them are in agreement with a lower value for H0. They are cosmology dependent. And then we have also the BAO measurements that, combined with the big band nucleosynthesis, give a lower value for H0 as well. And in this case, these measurements measurement is CMB independent, but still cosmological dependent. But we have also many late time measurements. We have the supernovae calibrated with Cepheids, and this is the Schu's value. We have the measurement, the supernovae calibrated with the tip of the Decaying branch, and we can see that this is the measurement by Friedman et al. That is well discussed because it's in the middle. And a few days ago just came out this new measurement. As you can see, the difference is small, is slightly shrinked the error bars, and is exactly in the middle, so can't really discriminate or say anything about this tension. Then we have a supernovae calibrated with Miras, the mega masers, and in this case we don't need a distance ladder, so this measurement is independent from the previous one. Then we have the measurements based on the Tully-Fisher relationship, and these are calibrated with Cepheids and tip of the Decaying branch, the surface brightness fluctuations, and again these are calibrated with both, and in particular this Blakeslee et al., that is a measurement of January, gives exactly the same value for this measurement calibrated with Cepheids of the tip of the Decaying branch. Then we have supernovae second type calibrated with both as well. And finally, the strong lensing measurement. Again, this has been discussed because the previous measurements were much stronger, more in agreement with Schu's, but they were assuming a mass density profile that was a power law or Navarro-Frank-White. Once we remove this assumption, we have larger error bars, and this is the new measurement that you can see that can be again agreement with everything because of the large error bars. So this is not cosmological dependent, but still astrophysical dependent. Now we can try to combine them together. We have to be careful because of course they are correlated, but combining them in a smart way, we have attention at about 6 sigma. We can do a jackknife of the results, removing one of the measurement, and if we remove the most precise one, the tension, that is the Schu's measurement, the tension is still at 5 sigma. If we do the same, removing 2 groups of measurements, and we take the one with the largest error bar, this is obtained removing Cepheids and strong lensing, and the tension is still at 3 sigma. So this tension is really robust. This is an updated plot with the new measurements and that you can find in our review. And you can see this is Planck, the light pink band. This is the Schu's measurement, the CN1. Okay, the indirect measurements are on this side and the direct measurement on this other side. Okay, you can use this tool here to make your own plot. If we filter this plot in order to have just the measurement of the Hubble constant with error bars less than 1.5 kilometer per second per megaparsec for the indirect measurements, less than 3 for the direct one, you can see that they are consistent at both ends of this plot. And so for this reason, a solution should should explain multiple observations in a rigorous way. This came out just a few days ago, is in this review by Wendy Friedman, and you can see how these measurements are converging towards the same value. The point here is missing what is measuring what, because it's true that before there was a more noise, but the tension was within the same type of measurements, and so this is indicating a systematic in the experiments. Now there are no late time measurements below the indirect ones, and vice versa. So it seems unlikely that a single error can erase completely all the tension, and also multiple unrelated systematic errors can cancel completely the disagreement we see. So another possibility is to change the model because the indirect constraints are model dependent and assuming the standard model. So let's see what happens if we modify the pillars of the standard model. First of all, we can start with the dark matter. And for example, the classical extension is modifying the effective number of relativistic degrees of freedom. And you can see that in order to be in agreement with the value measured by shoes following the direction of the correlation between this parameter and the Hubble constant, we need something around 4. And this is ruled out at many sigma by the new Planck results, including polarization. So even if we vary the energy effective number, the tension with the shoes measurement is still above 3.6 sigma. Another possibility is to consider extensions in the dark energy sector, and the classical one is to vary the dark energy equation of state. So we are replacing the cosmological constant with this dark energy, and again we can solve the tension. In this case, we can solve the tension, but at the price of a phantom dark energy with all the theoretical problems that this has. So here you can find a list, a classification of the formally successful models in solving H0. This is considered Planck only. So we assume this model, we derive the constraints within this model, we compare with H0, okay, without anything else. In this case, we can see that the excellent models that can solve the Hubble constant tension are late time modification of the expansion history, like the dark energy, the phantom dark energy, while the early time modification of the expansion history, like energy effective number in the dark energy, okay, are less promising. But let's look one precise one example between them, and to be as much democratic as possible, I will focus on just my the models that I studied. So here we have the Parker vacuum metamorphosis, and this is a first principle theory motivated by quantum gravitational effect that can mimic a phantom dark energy. And we can see that the expansion behavior above the phase transition is matter plus radiation plus curvature plus something that is constant, and below the phase transition is something that rapidly reshifts away like radiation, and with the transition given by this combination of the parameters. So in the original model, we don't have the cosmological constant, so we fix this to 0. We have this relationship between the matter density and the massive scalar field. So we have exactly the same number of degrees of freedom as the lambda Goddard matter model. And the other possibility is to include the cosmological constant high redshift, that is the expectation value of the massive scalar field. But we have to assume that the transition happens in the past and the dark energy is always positive. In this model, we have the effective dark energy equation of state that is phantom, multiply phantom in the past. In the case without the cosmological constant, there is no dark energy above the phase transition. So if we analyze the cosmological data within this model, in the original model, we don't solve the tension, we have H0 exactly 74. The problem is that the chi-square is much worse, so is plus 95. This means that we can't recover the shape of the expansion rate at low redshifts. And the same is happening if we include the cosmological constant. So for all the datasets combination, we obtain exactly the value measured by shoes, but with a much worse chi-square. What is happening here? That BAO and Pantheon are measuring this combination between H0 and the sound horizon. So if we want to be in agreement with a larger value for H0, we need a lower value for the sound horizon. If we want to be in agreement with the CMB with a lower value of H0, we need a larger value for the sound horizon. So something that is a late time modification of the expansion history, like a phantom dark energy, moves along this line, so can increase H0 without moving the sound horizon. So we need something that is along this line of correlation that can reduce the sound horizon and at the same time increase the Hubble constant. Unfortunately, the models that have been proposed, like the energy effective number or the early dark energy, can't solve the tension below 3 sigma if a prior on the Gaussian prior on H0 is not included. So this is how the classification is modified, taking into account that we don't have just Planck, but also other cosmological data sets. So this is Planck plus something else, and you can see that between the excellent models, we have more early modification of the expansion history. So again, let me focus on just one of these particular model, that is an interaction between dark matter and dark energy and non-gravitational, similar to what we saw before, but now proportional to the dark energy density. So if we assume this model, we have a flux of energy from dark matter to dark energy, so less dark matter, just an upper limit and 95% confidence level. But the CNB is measuring through the peak structure extremely well this combination, that is the matter density and the Hubble constant. So we have, if we have less dark matter, we need a larger value for each knot, and this is the reason why we can naturally solve the Hubble constant tension. And if we combine now this model with a prior on each knot, we have more than 5 sigma, 5 standard deviation of evidence for this coupling. Now we can be worried about the structure in the universe, but the growth of the dark matter perturbations is larger in this kind of the interacting models, because we have a suppression of the friction term and the enhancement of the source term. But when we add the BAO, the presence of a coupling is still there at 1 sigma, so with a lower statistical significance, and we have that the tension is restored above 2 sigma, 2.4 in particular. Now, at this point, it's difficult to understand if this is an actual residual tension or just a statistical fluctuation, because the BO are formed here at recombination, but we are measuring them here, and in the data reduction process, to extract the results in many points, we need to assume a model. The model that we assume is the lambda quantum matter one. So these BAO measurements are model dependent, and we don't know their reliability in extended cosmologies that are really different from the lambda quantum matter one. The reliability has been tested for models that can be parameterized by W0 WA, for example, but for this kind of the interacting cosmology that is excluding the null value at more than 5 sigma, we don't know how to handle the PAO data. So we have to be careful to rule out a cosmological model that can solve the tension just because this is the disagreement with PAO. So finally, let's move the third pillar, the inflation. Has been proposed many particular primordial power spectrum that can solve the Hubble constant tension. Now, here I want just to focus on the Harrison-Zeldovich model that has been proposed well before the formulation of inflation and corresponded to a perfect scale invariance of the fluctuation. That means that the scalar spectral index is exactly 1. So we have one less parameter than in the lambda quantum matter model. So this model is less complicated than the standard model. And if we assume this Harrison-Zeldovich scenario, we obtain H0 large and in agreement with the standard value. Now, even when, yes,
just a minute.
Now, yeah, even when we consider the Nugent effective number again, we have a much larger value for H0. So we can solve the tension, and this is true also if we include the BAO data. So summarizing, we have early modification of the standard model, but unfortunately this can't solve completely the Hubble constant tension. We have late time modifications of the standard of the expansion history, but these are in disagreement with BAO and phantom data. We have extremely different model from the lambda quantum matter one. We don't know how to handle the BAO data in this case, so we have to be careful to rule out these models because of BAO. We have a possibility to change the inflationary scenario, and if we don't have inflation, we have an Harrison-Zeldovich spectrum, we have a less complicated model, we can solve the Hubble tension. So if we look at this plot now, you can see the density of the proposed cosmological models. Here, there are just 180 data points, and these are the models for which we can, for which we found the data analysis. But the model proposed to solve the Hubble tension are at least a factor 2. In order to solve completely the tension, we need to be in agreement with this cross here and this cross here, and at at the moment, there is no specific proposal that makes a strong case for being highly likely far better than all the others. So we need more observations, and we need a better investigation of alternative theoretical models and solutions. So thank you. 1 minute before.
Very nice. Eleonora, you finish in time. All right. So any question, please? Or comment?
If I may, I have a couple of questions. The first one is, well, first of all, I completely agree that in the case of interacting dark energy, BAO might be unreliable. But as you pointed out before in your presentation, it's really the combination of BAO and Pantheon that kind of kills the late time evolution, right? And looking at your tables, even Planck plus Pantheon already strongly disfavors the model, right? So it's not really about BAO being unreliable, it's more about the model itself.
Yeah, but Pantheon is agnostic about H0, no? It's just a magnitude redshift relation.
No, you're perfectly right. But if you look at your table, Planck plus Pantheon is already kind of killing the model.
Yes, but we have still this indication for a coupling different from zero, from Planck plus Pantheon. Okay, so when we are adding BAO, we have larger error bars, so we are having stronger error bars. So we don't know how this is going to move. Okay, in which direction? More in agreement with Planck alone, or more in agreement with zero? That's my point. Okay, so we have this that we have still an indication at 1 sigma, and if we let the curvature fit to vary, the indication is above 3 sigma, for example.
Sure, no, I completely agree. Yeah, you're perfectly right. Still, I mean, it's just to discuss it with you. It's not really a criticism. It's really more. Even if you have a detection with at 1 sigma with Planck plus Pantheon, you do not really solve the H0 tension, but you make the sigma tension significantly worse. So it would still not be under your excellent models, even if you say BAO is unreliable, right?
Yes. My point is just if we have something that is borderline, that this needs more investigation. Okay, we can't just rule out everything.
Yeah.
Okay,
no.
That's my point. My example are about this. Okay, we can't just rule out something because in disagreement with this specific data set. Okay, because of course they are not completely reliable. Systematics can be everywhere. Okay, so we have just to investigate better and more deeply these cosmologies that can give an indication for a solution. Okay, as you saw, probably there are more than 300 different models that have been proposed. So
no, yeah, absolutely, you're perfectly right. Yeah. Okay, yeah. Thank you very much.
Thank you.
Leonora, I'm confused with this parameter psi. It is the parameter that goes in front of the source Q, psi times H and rho X, right? Because in your feeds it appears very, very high. I mean, 10 to the minus 1. Yeah, okay. It is this one.
Yeah. So
exactly.
it's the like as before, but instead of the matter here, there is the dark energy, and this is giving this completely different result. Okay, because we have less dark matter and more dark energy.
It's pretty large. I mean, we usually obtain 10 to the minus 3 for this parameter, not.
That's because we have the dark energy here. Okay, if you.
Yeah.
Yeah.
Okay. If you would put here dark matter or total matter, then you would get much less.
Yes.
Yeah. Okay. All right. And you get minus.
Yes.
And this minus, let me see, it corresponds to decay of vacuum into matter, or
yes,
or matter into vacuum. No, vacuum into matter.
No, matter into vacuum.
Matter into vacuum, exactly.
Yes.
So this is opposite to the second principle of thermodynamics.
Yes, exactly.
So, yeah, which is not very nice.
Okay. Yes, just an example of why we have to be careful with the BAO and in general with data sets that are completely okay, that are derived under the lambda golden matter assumption. We can have something that is completely different, and in that case, we can just say, okay, this is in disagreement with that. It was just an example.
Yeah. Okay. So very good. So in principle, if there is, unless there is a very quick question, we should move on. And
Hola, Peter. ¿Cómo estás? Bien, Peter. Bien,
Sorry?
Peter, muchas gracias. Yo te iba a llamar.
there is some noise or some comments. But okay, so we move on, and I would call Alessandra Silvestri, please.
Yes. Hi.
So she's going to talk on Hubble speed from first principles. So please,
Yes.
you can
Hi.
start.
Can you see my slides?
Yes, I can.
Yes. Perfect.
So please go on.
Okay. Thank you for having me here. I'm a first-time learner when it comes to H-Naught. And actually, this is some work that has been done in collaboration with my postdoc. I will mention him also later on, Fabrizio Renzi. He was really the driving force behind this work. I'm going to give a very basic presentation, trying to go through the steps of what we did, and all that I will talk about can be found in this paper that we have on the archive, with basically the same title as for this talk. So I'm going to start with something very basic, which is the concept of distances in cosmology, and the fact that if we look at the comoving distance, written in particular in this way here, where I separate h into h0 and e, the same parameter, the same function that Luca used before, basically the expansion, you can see that there's two factors that are conditioning a distance, the value of the Hubble parameter today, but also the cosmological model and how it evolves, basically how H or E of C evolves over time. So here E of C, I just want to give an expression for E of C, because later on I will get to the quantity that here I'm calling X. So I'm going to write, even though I don't use any of this until the very end of what I will present, I don't assume really cosmological modeling in deriving H0. I will use a cosmological model at the end to show some result about X of C. So I'm going to write it as some dark matter component, radiation, and some X component, which can be our beloved dark energy. It would be X equal 1 if it's a cosmological constant, but it can really be many other things. It can be modified gravity, it can be some spatial curvature, something that goes into our model beyond dark matter and radiation. So, of course, we do not measure, we do not observe the comoving distance. What we really observe are typically either luminosity distances, which are based on flux measurements, or angular diameter distances, and this is extremely well known to all of you. So I will go very quickly over this just to present some expressions that I will use in the next slides. So luminosity distance used to be all about supernovae. Now it's we're getting very excited also about standard sirens, but I will use supernovae in this talk. And so I will often refer to the apparent and the absolute magnitude of supernovae. And in particular, in the next slide, I will use this combination, I will use basically the combination of these two expressions for the absolute and the apparent magnitude in a way where I can remove the need of calibration of the absolute magnitude. And what I really get out of the apparent magnitude measurement of supernovae is is the combination H0 dl. And on the other side, we have angular diameter distances. We have already seen them in the previous talks based on standard rulers. And in particular, in this work, we have been using BAO measurements. And the way we will combine them, we will use them is combining the line of sight and the transverse measurements in such a way to get the RS, the sound horizon at drag epoch, out of the equation. And so get something that does not really need anchoring. So in a pretty general way, with very few assumptions that are the fact that we have a metric theory for gravity and that photons propagate along null geodesics, and there is a number conservation for photons, we can derive what is known as the distance duality relation. So that basically tells you what's the ratio between luminosity distance and angular diameter distance, how it scales with redshift. And if you combine them like here, the L divided by the A times 1 plus C square, then you find that this ratio is 1. Or more generally, you can call this a function of redshift, eta. And there's also some measurements that have some constraints that have been put on it of the order 10%. But I'm really just going to assume from the theoretical point of view that this eta is 1. That's my assumption. And then if I set eta equal to 1, I can do some very basic tricks and multiply and divide the expression above by H0, and I can get the following expression for the Hubble parameter today, which becomes a combination of some quantities that I highlighted in the slide before. So the luminosity, the uncalibrated, basically, information from supernovae, so H0 times dl, the unanchored combination of data from BAO, H of C times the A. And then, of course, if I really want to get H0 out of this, I need to factor in also some measurement of the Hubble parameter. And since we wanted to be to do not make assumption about the cosmological model, we use cosmic chronometers measurements of the Hubble parameter. So let me be a bit more specific. So in the slides that will follow, I will show some results that we got out of this equation, combining indeed the BAO measurements, in particular 7 data points from both eBOS and the Lyman alpha, and the Pantheon compilation of roughly 1,000 upper magnitude measurements from supernovae, and a compilation of 30 measurements of H of C from cosmic chronometers. Now, I went the other way around. Cosmic chronometers are basically a way of using the differential age of galaxy population and combining that with spectroscopic measurements of the redshift of such galaxies. And the ideal candidates are massive galaxies where basically the star formation has stopped at high redshifts, higher than 2. Let me mention again Fabrizio. This, especially what will follow, is some technical aspects of the work, and it's all work of Fabrizio, who's a postdoc with me here in Leiden. So the idea is we take this set of measurements, supernovae without calibrating them, BAO without anchoring them, so without introducing some complementary information about the sun horizon, and cosmic chronometers. And we try to use the formula provided us by the distance duality relation to extract H0. Now, some technicalities, if you want. So the data that we're using cover more or less the same redshift range between today and 2.5. But that's not, of course, we do not have data points exactly at the same redshift for all these different compilations. So the way we proceed is that we choose the redshift of the BAO sample as our reference points. And we use Gaussian process regression techniques to reconstruct, to basically fit the supernovae and the cosmic chronometer data, and hence extract from there values in forms of posterior distribution function, values of the luminosity distance of supernovae and h of c of cosmic chronometers at the same redshift as the BAO data. So what we really do after doing this fit using Gaussian process techniques to H0DL and H of C of cosmic chronometers, we have basically posterior distribution functions for these quantities, and we draw 10 to the 4 realizations for each of those, and we combine them using the distance duality relation expression to get and combine them, factor in also, sorry, at the 7 redshift, factor in the BAO information, and overall combine everything using the DDR to get realizations of H0. So to basically construct posterior distribution function of the Hubble, of the value of the Hubble parameter today at the, as derived from the data at the different 7 redshifts. Of course, we do expect to have consistent values of H0 at the different redshifts. And as I will show you in the next slides, they are a bit consistent within error bars. There's some true outliers a little bit. I will say more about that. Once we have this posterior distribution function for H0 at the 7 original data points of BAO, redshift of the BAO data points, we multiply them together in order to get a single PDF for H0, from which we extract, using some inverse transform sampling method, we extract the mean and the variance. I will refer to this method as GPMC just because basically combines both Gaussian processing techniques, but also Monte Carlo sampling technique. I just want to stress that we do this within the redshift range of the data. So what we really use is interpolation of the data, Gaussian process to interpolate, not to extrapolate. And so these are the results. The different shaded curves are the different posterior distribution function of H0 as obtained from using the combining supernovae BAO and CC at the 7 redshift as listed in the top left. And as you can see, the 7 distributions are consistent. There are those in green corresponding to the Lyman alpha, to the redshift of the Lyman alpha points that look a little bit like outliers, like they tend to lower values of H0. So we extracted 2 different final values of H0 out of this, one combining all 7 PDFs, the other one combining only 5, so removing the 2 lower values. And the values that we obtain are around 69, so 68.6 in one case and 69.5. Plus or minus 1.5 or so in both cases. Now, this is just showing again the 2 results that we get for H0. I call conservative the one in which we remove the Lyman alpha points. And we remove them, and why do we say being conservative? We remove them because those 2 points are at a quite high redshift, and we do not have supernovae and cosmic chronometers data points in that for those redshift values. So we are stretching a little bit the Gaussian process fit outside of the region of where the original data was. So then we become more kernel dependent. And this is just showing the 2 results in comparison with other popular values of H0 from Shoes, Planck, and the Carnegie Chicago Hubble project. So that is the calibration of the supernovae with TRGB. And you can see that we are basically spot on that value. Correspondingly, so we have avoided calibrating the supernovae. So we have, but we can now, having an H0, the way we have inferred it, we can go back to our supernovae value and infer an absolute magnitude. And compare that, for instance, with the absolute magnitude of shoes for the same set of supernovae. And we find a shift, which is of 0.138, which is consistent with a similar shift that was suggested by in a paper by Efstazio when he was comparing calibration of supernovae with Cepheids and the TRGB method. So that said, let me go back to the outliers and this why we remove them. I already mentioned why we remove them, but then I gave you the two results and compared the two results for H0. So the first question that one could ask by looking at these different PDFs is there a redshift trend in H0? So why, if I use, if I combine my data at lower redshift, I tend to get values of H0 that are closer to 6970, but I have this sort of two outliers that if I combine the data that are at higher redshift—
3 minutes, Alessandra.
Yeah.
3.
Yeah, I'm basically done, thank you. That
No
use the
problem,
Lyman alpha, I tend to get a lower value. Is there really a trend in H0? And what would that mean even? So I want to make a point about that. And we think, at least in our analysis, we think that this is, of course, not really a trend in H0, but the fact that this thing shows up is due to the fact that when we use the distance duality relation, the way we are using it to infer H0, it's we are really, besides assuming the validity of it, besides assuming that actually eta is equal to 1, we are really assuming that the two probes that we are combining, in particular the tracers of the luminosity distance measurements and the DA measurements that we get from BAO combined with CC, are equivalent tracers of cosmic expansion. In reality, there is a sort of lag. If there is any dynamical feature in our H of Z, any deviations, for instance, from lambda CDM, there is a lag in the way in redshift between when supernovae, which basically are sensitive to an integration of H of Z, pick up this dynamical feature with respect to when cosmic chronometers, which are a direct measurements of H of Z, pick up such a feature. So, and indeed here we are showing a comparison of the mu, which is m, little m minus m. So it's the difference in the absolute and relative magnitude of supernovae, and also with the plot for the angular diameter distance, is comparing the data points and our GP fit, which is the solid blue line with the contours, error contours in light blue, with the lambda CDM prediction, where I think, if I remember correctly, we have used our best fit H0 to get a lambda CDM, the lambda CDM prediction for these distances. It's not that relevant anyhow. So, but you see that there is a sort of lag in the way the departure from lambda CDM is picked up. And indeed, we have tried using the data sets to reconstruct also the function x of z, that one that I show at the beginning, entering in E of z, the cosmological model. So anything that would be different, or well, it could be x of z is 1 if it's a lambda CDM, if it's a cosmological constant, and it's something different from 1 and evolving in time if I have, for instance, dynamical dark energy or many other things. So this is my last slide. I actually don't have conclusions, so I'm just going to make a few comments about this. I'm not claiming any detection, any significant feature, but I still wanted to say there is a mile. So this is buried, of course, right? You see what I'm showing you is I'm claiming that I'm asking you to basically look at the difference between the blue solid line and the dashed black one. That difference is buried within the 1 sigma contour. So it's not really, perhaps we shouldn't even be discussing it, but it's something that in principle could persist and could become more significant with upcoming data. It's also in line with other more statistically significant finding about possible dynamical features in X of Z. And it is really what is behind this trend that we saw in the values that we infer for H naught. And I don't really have conclusions because I think it was a very self-contained topic. And so I will just stop here.
Very good, thank you very much. So if there is any question or comment, it's now the right time.
There are a couple of raised hands, but maybe I was not the first.
I don't see them, so.
I think,
Luca, please.
I think Benisti was first, so please.
It was first, okay. If you
Yes,
say so, please, David.
Okay, thank you. I wanted to ask, I mean, which kind of kernel, if you remember, which kind of kernel you use for the Gaussian process regression? I mean, because there
I
are
like if you remember.
few different behaviors.
Yeah. So we try different ones, and I think we settle on the so-called matter kernel. Don't ask me much more about that. But we could see that the difference was really negligible within the Reshift range over which we had all data. Of course, as we were going a bit at higher Reshift, where the Lyman alpha points are, the differences between the kernels were showing up a bit more.
That's fair. Thanks. Okay. Thank you.
Sure.
Okay, so Luca.
Yeah, thanks, Alessandra. A very, very simple question. You say that you can go back and test, and measure the absolute magnitude. Can you also test whether the absolute magnitude is a constant?
Oh, I'm not so sure. Yeah, probably I could translate what we projected into X of Z. Maybe I could do a similar exercise for the absolute magnitude.
Well, it should be possible, right?
Yeah.
You do a different ratio, then you check whether it's really
exactly for each Yeah, I think it could be.
May I ask for that question, because there is some ambiguity, right, in between H0 and the value of M. So for the Gaussian process, you can get like model independent approach for mu, but still you have some ambiguity in between M and H0. So I think, no? Or...
The H0, the AB, what I call AB, you're saying, or I'm not sure what is H0. Are you saying the intersect in the
so
magnitude?
there is ambiguity in between MB and H0, right?
So yes, thank you. I didn't really specify that indeed. So for we fixed this thing AB. So we focus on MB, and so in this equation that I'm using down here for MB, translating basically the measurement into H0DL. Yes, I have fixed AB with a Gaussian prior on it. So taken out of some Schulz paper. Yes.
But still, you can fix now H naught and see whether MB or MB plus 5 AB is a constant or not.
Yeah, I could do that, I think.
Okay, thanks.
Yeah.
Okay. So thank you very much, Alexandra. So we move to the next speaker. Yes. So the next one is Ariel Sanchez. He is going to talk on Let Us Bury the Prehistoric Little H. So please, you can start.
Can you hear me now? Yeah.
Yes, I can see.
Yes, great.
I guess everybody.
Thanks. First of all, yeah, let me thank the organizers for inviting me, and this is a pleasure, very interesting session. And yes,
thanks a lot for coming.
In this talk, I will be giving some arguments against this common practice in cosmology and observational cosmology of using these units to express distances in megaparsecs over H units, as I will try to convince you that this has led to some crucial misconceptions related to the way in which we normalize models, theoretical predictions for the matter power spectrum. And then what I will do today is, well, I will describe some of the results that are presented in this paper that I published last year. I will focus here on the implications of these misconceptions on the so-called sigma 8 tension. Okay, so let me begin. Of course, you know this, but what is the origin of these megaparsecs over H units in cosmology? And the origin is that when we analyze galaxy redshift surveys, what we actually measure are redshifts and angular positions. And in order to do a three-dimensional clustering analysis, the first thing that we need to do is to transform those redshifts into distances. And in order to do that, we need to assume a fiduciary cosmology. So this is the expression that gives the co-moving distance as a function of redshifts. And for very low redshift samples, as the first galaxy redshift surveys that were built 20 years ago or more, much more actually, we can approximate this co-moving distance redshift relation simply by this expression. So then if we write H naught in terms of the little h parameter, when we express our distances in megaparsecs over H, the clustering measurements that we obtain are completely independent on any assumption of a fiduciary cosmology, right? So H is the only parameter, the only cosmological quantity that enters here. So when we express everything in megaparsecs over H, our measurements are independent of this assumption. So this is valid, of course, only for these very local samples, low redshift samples, but this practice is extended and is now also applied to all present-day samples that cover much higher redshift, that probe higher redshift and cover wider redshift ranges, like the Varying Oscillation Spectroscopic Survey. This is an example of measurements, anisotropic clustering measurements. So these are the correlation functions in the direction perpendicular, intermediate, and transverse, and the line of sight direction, parallel to the line of sight direction from both in this redshift range. And all of these measurements are also expressed in these units, megaparsecs over H. But of course, at this redshift, it is not possible to use this approximation, and we still need to assume a full set of cosmological parameters in order to compute to estimate our distances, to transform redshifts into distances. Still, the argument is that, well, at least we don't need to assume a specific value of H, but the use of these units doesn't change anything in the analysis of this data. There is no step that it would be different if we express the data in megaparsecs over H units. Okay, so I mentioned that this is related to the assumption of a fiduciary cosmology. So let me just review very quickly what is the impact of the assumption of a fiduciary cosmology in our clustering measurements. And this is related to the so-called Alcock-Paczynski distortions that Luca mentioned in his talk. So let's assume that this represents our galaxy survey. So when we observe our distances, we want to estimate clustering measurements. So we are interested in the separation vectors between different galaxies. But when we assume a cosmology, the cosmology that we assume is almost certainly wrong, at least slightly wrong. So that means that the distances that we infer to these individual galaxies are wrong. And this distorts the separation vector between these galaxies in a way that can be described by these rescaling factors of the components in the parallel to the line of sight direction and perpendicular to it. And these rescaling factors are known as Alcock-Paczynski parameters. These are given by the ratios of the angular diameter, the co-moving angular diameter distance, and the Hubble parameter in the fiduciary cosmology and the true cosmology, evaluated at the mean redshift of the sample. Now, it is clear that if we use in our data and in our theory predictions units of megaparsecs over H, then these quantities must also be expressed in these units, as the ratio of distances into two cosmological models is not the same whether if we express them in megaparsecs or megaparsecs over H cosmologies. So now, if let's say that we have a theoretic prediction for the two-point correlation function, the anisotropic two-point correlation function, before we can compare that theoretical prediction against our measurements, we need to take Alcock-Paczynski distortions into account. And this can be done easily by evaluating our theory predictions at the scales that are mapped into the particular scales in the fiduciary cosmology where we have our measurements. Now, it is also common to express theory predictions before we account for Alcock-Paczynski distortions in them also in megaparsecs over h units. That means that these scales are expressed in megaparsecs over h units. But if we do that, the factors of h appearing in S simply cancel out with the factors of h that appear in these Alcock-Paczynski parameters. So what this is just saying is that, of course, there's no difference in whether if we express this theory or this data in megaparsecs over h or megaparsecs, as we will obtain in the end the same results. And this is just saying that the information content of these measurements doesn't depend on the particular units in which we express them, but also it implies that the fact that we can express our measurements in megaparsecs over h units without assuming a specific value of h doesn't imply that we can only obtain measurements, recover constraints on quantities that also refer to distances expressed in these units. Okay, so I mentioned that it is common to express theory predictions also in megaparsecs over h units before we account for Alcock-Paczynski distortions. These factors are irrelevant. So this is a plot, for example, of models of a linear theory power spectra for 3 lambda CDM models. I will describe them in detail in a second. But these are expressed in megaparsecs over h units. These factors are irrelevant with respect to cosmological constraints, because before we can compare these models against data, we need to account for Alcock-Paczynski distortions, and these factors of h will simply cancel out, as we said before. So let's try to see, what I will try to convince you is that expressing theoretical predictions in megaparsecs over h obscures the true impact of the value of h on the matter power spectrum. And this has some important consequences. Okay, so these are then 3 different lambda CDM models. The red line is basically a Planck lambda CDM cosmology. And the other 2 models are obtained by fixing the physical baryon, cold dark matter, neutrino densities, and the amplitude and spectral index of the scalar mode. And I only changed the value of h. So when a lambda CDM, these are all lambda CDM universes, the way to do this would be to change the dark energy density, right? Okay, and what we see is that expressed in these units of megaparsecs over h, they look different. The BAO features are out of phase, also the turnover scale is different. But if we express the same models in megaparsecs units, this is what they look like. So we see that the BAO features now are perfectly in line. Also, the turnover scale is exactly the same. And these models only differ in amplitude. And of course, this should be expected, although some people find this result surprising. This should be expected because what we are doing is we are fixing the parameters that control the shape of the transfer function and the tilt in the spectrum. But then we realize that these models only differ in their amplitude. And the standard reaction to that would be, yes, well, we can normalize them to the same amplitude using the value of sigma 8. Sigma 8 is, measures the amplitude of density fluctuations at a scale of 8 megaparsecs over h. So this is a crucial thing. And when we do that, if we normalize the same power spectra to have the same value of sigma 8, this is what happens. So what you see is that the amplitude mismatch between these models is actually increased, right? This happens because when we vary the value of h, the value of sigma 8 changes due to 2 effects. First is the change in the amplitude of the power spectrum itself. So as we said before, for example, in these models, lambda CDM, if I change the value of h, keeping the value of the physical matter density constant, what I'm changing is the dark energy density, so that will change the amplitude of the power spectrum at a given redshift. But the value of sigma 8 also changes due to this second effect, that is the change in the reference scale of 8 megaparsecs over h, which corresponds to a different scale in megaparsecs for each one of these models. And this second point is the origin of several problems that have lots of implications. And it's why I think it's not the best idea to normalize models of the power spectrum in terms of sigma 8. So you see, essentially what we are doing is that for these cosmologies, 8 megaparsecs over H corresponds to a different scale. So what we are doing is by normalizing them to the same value of sigma 8, is that we are normalizing them to have the same amplitude at a different scale. This is not exactly a scale that is related to 8 megaparsecs over H. This is just for illustration, but this is essentially what we are doing. We are fixing their amplitudes on different scales. And then, yeah, the problem with sigma 8 is that it refers, we are using to normalize the power spectrum, a reference scale in units of megaparsecs over H, a scale that depends on a parameter of the model. So a better choice would be to use as a reference scale a scale in megaparsecs. So what I proposed in this paper is to use what we call sigma 12, which is the RMS of density fluctuations at a scale of 12 megaparsecs, not megaparsecs over H. Why 12 megaparsecs? Well, because for a value of H of 0.67, like the standard Planck lambda CDM fit result, 8 megaparsecs over H is roughly 12 megaparsecs. So the numerical value of sigma 12 is very similar to sigma 8 for the standard lambda CM cosmology, and this is also true for the redshift evolution of sigma 12. But for other cosmologies, these two parameters can be quite different. So you can see the same example that I showed before. If I renormalize this power spectra in terms of sigma 12, we see that they are identical. So these models have now different values of H and AS, but they are normalized. So these values combined result in the same value of sigma 12, and then we see that these power spectra are indeed identical. Okay, so this has lots of implications because sigma 8 is everywhere, and there are always these issues related to the fact that the reference scale that we use to measure sigma 8 depends on a parameter of the model. One very important is related to the way in which the results of the growth rate of structure from redshift space distortions are expressed. These are commonly expressed in terms of F times sigma 8. What I discuss in the paper is that this is not the best approach. The best way to really encapsulate the information content of redshift space distortion measurements is to use a combination of F times sigma 12 instead, and this changes the cosmological implications of redshift space distortion measurements. But I won't talk about that here. I want to talk instead about something that is more related to the topic of this session, that is the sigma 8 tension. So I don't need to review what is the sigma 8 tension here, but essentially it's just the fact that low redshift measurements tend to give, this is a plot of constraints on the matter density and the value of sigma 8. These are contours obtained from different lensing experiments. And if you compare the values of sigma 8 that are recovered for the same values of omega matter that are preferred by Planck, all of these data sets prefer lower values of sigma 8. But in view of what I saw before, sigma 8 has this hidden dependency on H. So let's see if this can have some effects on this plot. So this is my take on the same plot. These are contours on the matter density and sigma 8, assuming a lambda CDM cosmology, using the standard 3 times 2 point analysis from DES. This is DES year 1 data. This is an analysis from BOSS, where we use also a full shape galaxy clustering analysis. So this doesn't just use BAO plus redshift space distortion type of constraints. This is a full analysis of the data from BOSS. And then this is Planck. So all of these constraints use the same priors and everything. And this shows this sigma 8 tension. So the value of sigma 8 that is recovered from these data sets is lower than what is predicted by Planck. And this is often written in terms of this parameter S8. Okay, but sigma 8 has this issue that it depends on H. And if we look at the posterior distributions on H, 3 minutes, okay. The posterior distribution on H of these different data sets, we see that they're quite different. While Planck gives really narrow constraints on H, these other data sets, BOSS and DS, give much broader distributions. So that means that the posterior distributions on the meaning of this reference scale of 8 over H megaparsecs is also different for these different data sets. While for Planck, this is essentially 12 megaparsecs. For these other data sets, this cover a wider range of scales. And when we constrain sigma 8, what we are doing, the marginalized value of sigma 8 is an average of sigma of R marginalized over this distribution. So this means that the fact that these data sets have different constraining power on H, different posterior distributions on H, changes the meaning of this parameter for each of these data sets. So we can see what happens if we try to express these constraints, exactly the same chains, but in terms of sigma 12, right? So removing this ambiguity and this dependency on H. Here in the x-axis, I'm also using the physical matter density, also for the same reason, because the physical matter density removes the ambiguity on the value of H. It doesn't depend on H. And what we see is that this plot shows a different qualitative picture from what we saw before. In terms of sigma 12, DS is completely consistent with Planck, right? They both point to the same amplitude of density fluctuations at redshift 0, right? There's no tension here. The only data set here that prefers a lower value of sigma 12 is actually BOS. We are updating these constraints now. One of my students is running a new analysis with an improved model and combining BOS plus eBOS. We expect to have the results out soon. But I'm not trying to say that this solves the problem of the sigma 8 tension. All I'm trying to say is that we should be careful at interpreting differences in parameter constraints that depend on H, that are derived from data sets with different constraining powers on H. So if we see these distributions are completely consistent, right? There is no tension in H here, but the impact on sigma 8 is nonlinear, and then it can lead to apparent tensions in the data. So again, measurements that characterize the full tension between these data sets in the full n-dimensional posterior distribution will not suffer from this issue, right? So like the suspiciousness statistic, for example, but qualitatively, the sigma 8 tension has been interpreted as the suggestion that low redshift data somehow prefer a lower amplitude of density fluctuations than what would be predicted by Planck. And this is not correct. This is just an illusion that enters in our constraints due to the different constraining power on H on these data sets. So I will just finish here. I would like to remind you what are the main points of the talk. I said that the use of megaparsecs over H units, which essentially using megaparsecs over H units in our data or models doesn't change any step of the process, of the analysis process of this data, but their use has led to critical misconceptions. And a critical problem is the way in which we normalize the power spectrum, which should be normalized using a reference scale in megaparsecs. And then the agreement or disagreement between low and high redshift data regarding the amplitude of density fluctuations should be quantified in terms of this. A quantity using a reference scale in megaparsecs, such as sigma 12. And in general, it will take time, but I hope that we end up abandoning the use of megaparsecs over H units in cosmology, and we just use megaparsecs units everywhere. I know that will be difficult. Okay, so I will stop here and let me know if you have any questions.
Okay, thanks a lot, Ariel. So if there is a question or comment.
Yeah, there is a question.
I have actually one question. I have actually one question, Joan.
Yes, please.
Yes, Ariel, I guess you have had some feedback with people working in wave lensing and galaxy surveys. What are their arguments to continue using sigma 8 instead of doing the change to sigma 12?
Yes, so of course, the main argument, in my opinion, the main argument is just inertia, right? So it's easier to keep doing things the way they were done before. So yes, but there is really no argument. I haven't heard any argument against this. So people say, yeah, maybe this is correct, but yeah, so the arguments from with respect to the sigma 8 tension is essentially the same as what I mentioned before. Anyway, statistics like the suspiciousness that measure the full, the consistency between data sets in terms of the full parameter posterior distribution are independent on the parameters that you use, right? These are not affected by this issue. But this is why, so sometimes people measure differences in terms of S8 at the 3 sigma or more level, and when they quantify this tension in terms of the suspiciousness, these tensions are decreased. In the statistical significance of the tension is lower. But the main message regarding the sigma 8 tension that I want to stress is that we shouldn't interpret these different values in sigma 8 as a suggestion that different data sets point to different amplitudes of density fluctuations, because this is not the case. Right? So TS and Planck are in excellent agreement with respect to the amplitude of density fluctuations. Once we take into account, once we get rid of this ambiguity on the value of H. Yes, so to answer your question, the main argument against this is inertia. This essentially is at least from the Redshift space distortion community, that is where I've been most involved. I know that this is indeed the case, right? So it's the continuity with what has been done before. It's easier if results are expressed in terms of sigma 8.
Okay,
But
thanks.
You still said that this is not a solution to the sigma 8 tension. So why do you say so?
So is the solution to, if we label the solution as sigma 8, if we label the tension as sigma 8, yes, this is the solution to the sigma 8 tension. But this, if we quantify the tension or the agreement or disagreement between high redshift and low redshift data in terms of other statistics like the suspiciousness, for example, if you measure a 2 sigma difference in the parameter distribution, in the full posterior distribution of low redshift data and Planck, this is not solved by this. This is a different issue, but this tension shouldn't be interpreted as a difference in the amplitude of density fluctuations. I guess that we shouldn't call this the sigma 8 tension, right?
Okay.
The tension must be at some level. If there is a difference in the cosmological constraints that are recovered from these data sets, it is not in the amplitude of density fluctuations. This is.
Do you think that the language will change in the near future? I mean, not to call it sigma 8, but sigma 12 or whatever.
It will
take a long while.
It will take a long while, but I think that this is also a generational issue. So I would like to emphasize this to the young people in the audience. If people haven't written lots of papers in terms of sigma 8, maybe it will be easier for you to start using parameters using a reference scale in megaparsecs. It doesn't have to be sigma 12, but as long as it is a scale in megaparsecs, we will get rid of this issue. And this is important. This has important consequences.
Okay, thanks a lot for this talk. I suggest to move to the next one. Thanks a lot.
Thanks.
So the next one is by David Benisty. He's going to talk, on quantifying the S8 tension with redshift space distortion data set. So please, David.
Exactly. I'm only trying to put like full screen. Let me do like a new share full screen. Okay. So may I start?
Yeah, sure.
Yeah. Okay. Thanks. So my name is David Benisti. Now I'm currently a visitor in Frankfurt Institute for Advanced Studies, like short term also like in Ben-Gurion University as a postdoc. But soon in October, I will begin my fellowship at the University of Cambridge. So I have to mention this. And I'm going to speak today about how to quantify the S8 tension with 2 different approaches, like some comparison. Let's say I'm not going to solve, let's say, the tension or something like that very big, but only like to make some comparison that will give you hopefully some insights or some new directions of thinking in terms of Bayesian analysis, I mean the regular Bayesian analysis, and also some machine learning method. Okay, so BA by Bayesian analysis and ML, some machine learning method, especially for Gaussian process regression. So let's begin, of course, with mentioning, I mean, the observed universe and which kind of origin of data set that we have today that we need actually to focus on. So we know that we have, like, of course, the inflationary period and also like the creation of the particles, but then we have like the universe when it was like very hot, and then we have like the release of the lights outside, the radiation outside. So this is like the cosmic macro background that we can detect today with a very large resolution. And then we have the matter domination and some cosmic dawn, or some like new epochs that actually today is like discussed in the community. And in nowadays, we have the domination of cosmological constant and the domination of cold dark matter, what's called the lambda CDM model. Now, so when we're taking a look, I mean, especially on the cosmic macro background analysis, how did it observed from the sky and from late time measurements, there are some disagreements, what's called tensions. So especially signs for dark energy that we have today, I mean, we have plenty of signs of dark energy, also from the CMB itself. I mean, because if you don't have like enough energy rate for dark energy, you don't have the same power spectrum, of course, but also you have the rate, I mean, in order to explain the expansion rate, so you have to include the cosmological constant inside. So also from the Pantheon dataset, cosmic chronometers, when you have only like the measurements, the estimation of the Hubble constant in different redshifts and baron acoustic oscillations and so on and so on, you have to include always the existence of dark energy inside, of course. And also in the perturbation level, so it's possible also like taking a look on perturbations from the early universe, what we mentioned, I mean, the cosmic macro background anisotropies, but also here today, I mean, we have more and more data from dark energy survey and large scale structure and other measurements that help us to quantify the perturbation level in our sky. So when we're saying actually like some tensions in cosmology, so the two famous tensions that we can speak of, I mean, this is the H0 tension and this is the sigma tension. So the H0 tension, as you know, and as other speakers discussed, this is the disagreement between the early measurement and the late time measurement of the Hubble constant. So even if you include inside, because you have an error bar for any measurement, so even if you include inside, I mean, plus 3 sigma, 4 sigma of error inside the measurement of the early time or the late time, still you have like some disagreement in between the Hubble constant measure or estimated value, because from the late time this is like measured, early time this is like estimated. But in addition to that, we have also a very known tension, what's called the sigma tension. And the sigma tension, this is like more than 3 sigma difference between the early and late time measurements from the cosmic macro background and the larger structure of the universe. So they would love somehow to take a look on this kind of tension with a very simple data set. So the presentation is going to be very simple in that sense, but I hope this is going to give you like some insights. So the S8 tension, and especially I am going to discuss about the S8 tension, the full quantity that quantifies also the sigma 8 and also the omega matter inside. So the S8, as we defined before, its matter fluctuations averaging sphere of certain radius. However, if we want to include inside the matter perturbations, so we can use, I mean, this quantity that combines also the matter density and also the matter fluctuations. So as you can see, and this is actually the data set that you are going to discuss today. I mean, this is the data set that you are going to use. So I collected from different surveys, I mean, around 50 data points from different redshifts. And they are in the range in between redshift 0 up to very close to 2, okay? So before I'm going to show, I mean, the results of Bayesian analysis or what also the Gaussian process regression may give, I mean, on this kind of analysis, you can see that if we take, I mean, the Planck observation and we evaluate the Planck actual values, okay? And we evaluate them, I mean, on very early times. So you can see like the Planck prediction. And I added, because of the values that comes from Planck are with a very low error bars. So the error bars on the blue line are very low. However, when I took like the Bayesian analysis on this kind of data set, because we can see like the error bars are very large. So the best fit, I mean, on this data set actually looks a bit different. I mean, this is only from the first taken look, I mean, on the plot. But as you can see, I added also like 5 sigma inside. So, I mean, the error bar still, it's a bit larger, but still there is some difference, which is like observed in our eye, okay, even for this kind of data set. So when we're speaking about the sigma attention, we have to speak about also a homogeneous solution and also like the perturbation solution. So in homogeneous cosmology, we can assume lambda CDM model, we can assume also like some different parameterization for dark energy. So for the simple possibilities, I included like the constant cosmological constant, but also some a small deviation from this kind of cosmological constant. So some dynamical dark energy inside. Okay, so this is the 2 models that I want to take a look and to analyze this data set. Now, in addition, we have to mention that I ignore radiation because, of course, we're speaking about a very, very large, a very low redshift. So, I mean, only in the early universe we have to take into account the radiation domination. Okay, so this is like for the homogeneous solution. Now, in the perturbative solution, I mean, if you take the Einstein equation and you perturb them, I mean, in the first linear order, so you can define what should be the matter perturbations. This is like the delta rho over the homogeneous density. And then after, if you assume a small scale approximation, so in small scale approximation, you don't have dependence on decay. Decay, this is like the momentum of A, like in Fourier space. But after some derivation, it's possible to show that the delta equation, the delta differential equation goes as following. So as you can see, and this is what I want to give as a statement, because everything you can read in the paper, but as a statement, what I want to keep in mind, that if I have an homogeneous solution, I have also like some prediction for the perturbative solution. Okay, so this is like the very successful theory of the cosmology. So there is a connection in between the perturbative solution and the homogeneous solution. And from that, after I derived the delta M, it's possible to show that the F sigma that we actually measure, this is actually comes from the first derivative of this delta matter. I mean, this is the derivative with respect to A, but also like with respect to N, like log of A in that sense. Now, besides this, we can, I mean, define 2 ways how to define our likelihood function or the chi-square. Because in one side, if all of the data set is not correlated, so the chi-square is going to be very intuitive. It's going to be like the difference in between the data of the F sigma 8 minus the prediction of the F sigma 8 from the model over the error bar of the F sigma 8. However, if we have some correlation, some hidden correlation inside, we have to take this into account. Now, the problem, because these are actually coming from different surveys, I mean, if you include like one survey, you have the correlation matrix, the efficient matrix as a data, like is given from the survey. However, if you have like a different service, so in order actually to test if there is like some correlation, I put by hand like a randomized correlation in between 2 points, where sigma I and sigma j are the error bars of the corresponding data points, but still like this is some random points. So I took like 25% random points in between different points that I had like in my analysis in order to see if there is some hidden correlation inside. Okay, so let's say, I mean, first of all, the Bayesian analysis for lambda CDM model. So, I mean, yeah, in one side, the omega matter value is a bit lower and the sigma 8 values are a bit larger, but again, I'm going to speak only on the S8 value, which combines the whole analysis. So as you can see, the S8, I mean, as like many different papers also show, but especially maybe this is because related to this collection of the data set that I took, the S8 is around 0.7. And when I'm assuming like some random covariance, So there is a slight change, I mean 0.96, but still, I mean in the error bars, there is no a big difference of the S8 itself. However, in Planck value, as you can see, this is much difference. I mean, it's like 0.8. So of course, I mean, which is very trivial for now, there is some tension in between the S8 value from the late universe to the early universe. Now, when I'm taking the WCDM value, so as you can see, in the case of WCDM, there is a possibility for increasing a bit the S8 value. And if I'm adding like some random covariance, this is actually changing the S8 by some value. But still, I mean, the tension exists. Okay, but still there is like some closer value, let's say, to the value of Planck. Now, and this is now the next step that I wanted to take a look. I wanted like to take a look some model independent approach. So I used the Gaussian process regression. So the main idea of Gaussian process regression, this is like to assume not something that related to the model, but to assume something that related to the functions. So you're assuming like some, let's say, only to give intuition, some distribution of many functions inside, okay? So this distribution may be, for instance, like a Gaussian distribution of covariance inside, or can be matter kernel or extended matter kernel because you have like a few kernels inside. And as you can see from different kind of distributions, you can define, I mean, this is like in the theory of the Gaussian process, I mean, the theory of machine learning, you define some loss function, which is very similar to chi-square function, and then you minimize it, and then you can actually get what should be the smooth behavior in between the points. And this is like a kernel dependent and not a model dependent. No, you don't have to assume some function that you try to fit, okay? Now, I have to give like some comment about this kind of method. And this comment, I mean, because I saw like many papers, I mean, in the community that try to use like this kind of method. And of course, this is amazing method, but still any method, there are some problems that you have to take into account. In one side, the Gaussian process regression has, of course, you have to assume always something. In this particular methods, you're assuming the kernel dependence, okay? So for different kernel, as you can see, there is a different behavior. I mean, the error bars and also like the smooth behavior, I mean, the mean value also looks a bit different or a lot different, I mean, different kernels. In addition, and this is some comment that I saw like in earlier presentations, but now I want to say it, I mean, we have to state it. After, I mean, as you can see, because you are assuming some distribution that looks like a Gaussian, okay, or based on Gaussian, the result is going to be a very similar behavior to a Gaussians in many cases. So as you can see, I mean, for instance, like if you take like the Pantheon dataset or the JLN dataset, or a Pantheon of different kernel, or if we take even the Hubble parameter, the cosmic chronometers dataset, after the dataset itself finishes, you have like some decreasing behavior. Of course, now this is not changing, I mean, if you're trying like to take a look on the initial value, but I cannot use like this method to describe the whole history of the universe, or even like for a bit larger redshifts, okay? So this point also we have to take into account. This is kind of not a perfect method, but still it's like model independent or kernel dependent. Now, so as you can see, I use like different kernels in order to find what should be the initial point, because from the initial point, I try to extract what should be the S8 value. So as you can see, because, I mean, this is also from the theory of cosmology, the FS sigma 8 in larger redshift should be lower. This is actually corresponding to the behavior of the Gaussian process regression. So as you can see, these are the initial values that I found with the Gaussian process regression of the S sigma 8. Now, even they use like different kernels, you can see that more or less the values are pretty stable. But
3 minutes, David.
Thank you.
Just
I'm very close to the end, thanks. So, but still, however, when we're taking a look on the initial measurements, I took like the initial measurements that you see here as the references downstairs. So this is like a very close redshift to 0, okay? So still you can see that there is a difference in between the F sigma hat and the values that I found with the Gaussian process regression, which again can be some systematic in the data or the data that I took or in the observation, because the error bars are very huge. Still, there is a difference, and the difference should be mentioned. So bottom of line, when I took like the initial points and I tried like to do like the same fit, so I found that in some kernels, the tension may be reduced a bit. Let's say from 3 sigma to 1.5 or around smaller than 2 sigma, let's say. So as you can see, this is like the S8 values. I mean, the S8 values that comes from lambda CDM, or here this is actually W, so I mean, this is, I think, a mistake. Okay, that comes from the Gaussian process method, and here you can see like the corresponding tension that I found. So when I'm saying tension, I mean like the average mean value over the square root of the error bars, and this is the Planck value. So as you can see, still there is a tension, but the tension may be reduced using the different kernels. So my conclusion, with Bayesian analysis, the regular Bayesian analysis, it's very clear that there is like some tension in between the Planck measurement and the late time measurements, if you're assuming, of course, lambda CDM model, not like different other models. However, if I'm using a Gaussian process regression, it's possible to decrease or to reduce the tension, but still the tension exists. And this is for me like some sign for, I don't know, new physics or like some new model beyond lambda CDM model, some interacting dark matter and so on and so on. But however, I mean that still, I think that there is kind of, let's say, method or like some way of thinking how to analyze in addition to regular Bayesian analysis to analyze data. So this is my final statement for now.
Perfectly in time. Thank you very much, David. Yeah, so questions, please.
Can I have one question?
Please.
Yes.
It seems that most of your results are based on the GP. Can you tell us what mean function did you use in your analysis?
What I don't understand the question. What do you mean by mean function?
Mean function in Gaussian processes.
Ah, okay. So I used, let me show you. So I used like first of all, like the Gaussian one, and also like the Mattern kernel with different.
No, this is the kernel.
Yes.
This is the kernel. I'm talking about the mean function. Okay, so did you use some ready-made code, or you use your own GP?
I used like the sklearn code. Yes, I used the sklearn code. Yes.
Okay, so do you remember which mean function they set?
No, it's a very good question.
So I think most of these cases, the mean functions are set to 0. And if you play with the mean function, then your results would be even more different. So that might be something maybe to consider. Yeah.
Thank you. Thank you very much. Thank you.
Yeah.
Any other question? I cannot see. So, all right. So that's fine. Thank you very much. Yes. So we move to the next speaker, Ed Macaulay, who is going to talk on measuring Hubble's constant with the inverse distance ladder. Please. So you may start, Ed.
Joan, I think he's not in the Zoom room.
He's not around?
It's not around. At least he has not entered yet the Zoom room.
Okay, so then we move to the next, and the next, I'm afraid, is you.
Okay.
So,
okay, let me share my screen.
So please, Adria, you now talk on early and not so early dark energy. What do cosmological observations tell us about them? So
okay,
you can start, please.
Yeah, thank you very much, Joan, for the introduction, and thank you all for attending this talk. Good afternoon. Yes, I'm going to talk about I'm going to talk about some constraints that we have obtained on the fraction of early dark energy, both in the pre and post recombination epochs, using two alternative techniques. The first one is based on a simple family of parameterizations of the early dark energy density. And the second one is, let's call it more model independent, because we just bin the ED density and put constraints on the fraction of ED in each of these bins using cosmological observations. So this talk is based on this paper that we hope will be finished very soon. We are in the last stages of the grading process. It has been written in close collaboration with Professor Luca Mendola, Valeria Petorino, Professor Christoph Petterich, and also in very close collaboration as well with the master students Jan Sen here at the ITP Heidelberg. So this is the outline of my talk. First of all, I'm going to briefly review the so-called ultralight axion-like ED models, which have become very famous in the last 2-3 years because they alleviate the H-knot tension, but as it was pointed out first by Colin Hill and collaborators last year, it is only at the expense of worsening the sigma 8 tension. So it is interesting to look for alternatives, extensions, or other models that can alleviate both tensions at a time. So what we have done is to include ED, that is an early dark energy component, also in the post-recombination epoch. This is not found in the early dark energy models based on ultralight axions. And we have done that considering quintessence models with scaling solutions. You know that in these models you find two plateaus in omega early dark energy, one in the radiation dominated epoch and another one in the matter dominated epoch. And we have explored a family of parameterizations, very easy parameterizations, but very useful as well. We have found that with these models, we cannot loosen the two tensions, the sigma 8 and H-knot tensions. So we have to explore more flexible shapes of omega ED. And we have done that by binning the dark energy density. I will provide details later on, of course. And I will end up as usually with the conclusions. So in this ultralight axion-like early dark energy models, which were discussed in detail in these papers in 2018, in the first one, these authors discussed the background and linear perturbations level, linear perturbations behavior of this model. And in the second one, they provided constraints on the model, okay? And they showed that it could loosen the H-knot tension. So this model is based on this scalar field potential. You can see here that depending on the power and the steepness of this potential changes. So if you want to study the dynamics of the scalar field in this model, you have to use, of course, Klein-Gordon equation together with the Friedman and the pressure equation. In a homogeneous and isotropic universe, it takes this simple form. So let us analyze how the scalar field evolves in this model. Deep in the radiation-dominated epoch, when the Hubble function is much larger than the typical mass of these ultralight axions, the term that dominates the equation is the friction term. And hence, the scalar field is frozen, and the potential energy density is just a constant. So the model behaves as a cosmological constant with an associated energy density, which is much larger than the one we measure nowadays with supernovae data, for instance. Okay, so this energy density has to be of the order of the radiation energy density at some epoch prior to the recombination epoch if we want to have an impact on the H-knot tension. Once the Hubble function goes below that threshold, then the scalar field acquires some dynamics. It rolls down the potential, and eventually it starts to oscillate around the minimum. And its equation of state parameter is just equal to 1/3 or larger, depending on the value of n. So as you can see here in this effective fluid description of the model, also suggested by Dolan et al., the energy density is just a constant, and then it decays when you go to scale to values of the scale factor which are much larger than this AC, which is typically when you find the maximum in the fraction of early dark energy. At the level of the perturbations, the sound speed of this fluid in its rest frame is equal to 1 when deep in the radiation dominated epoch, and then after this transition point, there is a difference between low and large scales. At large scales, c² is equal to 1/3 or larger, depending on the value of n again. And at low scale, c² is equal to 1. So as you probably know, this model is able to alleviate the H0 tension. Of course, Planck collaboration has measured with high precision the temperature CMB anisotropies, and in particular, the location of the first peak, which is related with this angle theta star. It is basically the inverse of the multiple at which the peak is located. And this theta star is the fraction of the angular diameter distance to the Dallas scattering surface and the sound horizon at the Baryon Dirac epoch, which, naively speaking, can be thought of as a ratio of the Hubble function before in the pre-recombination epoch, or at the last stages of the pre-recombination epoch, and the Hubble parameter. Of course, if you introduce an ED component in the last stages of the in the pre-recombination epoch, then you force somehow to increase the value of H0. Okay, but let us see what happens, because there are some problems. I have taken this table from Poulan et al., in which they fit the model using Plan 2018 CMB data, supernovae from the Pantheon compilation, baryon acoustic oscillations data, and the shows prior on the Hubble function. As you can see here, the model is of course able to increase the value of H0. Thus, it loosens the H0 tension, but okay, and this is due to a decrease of the sound horizon at the Baryon Dirac epoch. You have a peak in the ED fraction, which is around 3%, 7%, depending on the values of n. And this peak is located at a redshift around 5,000, more or less. So it happens before the matter radiation equality time. But the problem is that in order to accommodate all the data, you need an excess of cold dark matter in the late time universe. As you can see here, you can compare these values obtaining ED and the lambda CDM. And this automatically leads to an enhancement of the large scale structure formation processes, as it was noticed by Colin Hill and collaborators in this paper last year. So we can ask ourselves some questions. For instance, can other shapes of the fraction of dark energy help to loosen the tensions? And in particular, we could introduce an ED, a non-negligible ED component in the post-recombination epoch, because if it has sound speed equal to 1, then in natural units, then you would expect this to fight against the aggregation of matter by lowering down the value of sigma 8 or S8. It is also interesting to study what is the interplay between early dark energy and late time dynamical dark energy. There could be some degeneracies here. Also, what is the status of the H0 tension if it is formulated instead of using H0, the absolute magnitude of supernovae measuring the first steps of the cosmic distance ladder? So I will provide also fitting best fit values for M, and we will quantify the tension also using this parameter. And this is in connection with the talk by Ariel. So we will also provide values of sigma 12 and S12 in order to better quantify the tension in the large scale structure sector. So we have introduced an ED component in the post-recombination epoch using quintessence with scaling solutions. Okay, so these models are not new at all. They are from the late 80s. So, for instance, early dark energy in quintessence with an exponential potential exhibits scaling solutions with an ED fraction that takes this form, where the equation of a state parameter W is the one of the dominant component in the universe. It is equal to 0 in the matter-dominated epoch. It is equal to 1/3 in the radiation-dominated epoch. So you can see that the two plateaus in omega early dark energy are controlled by one single parameter. Okay, this scaling solution was found by Copeland, Liddell, and Wans in the late 90s. So, okay, so what we have done is, okay, let us produce two independent plateaus instead of two plateaus controlled by one parameter. We want to have two independent plateaus controlled by different parameters and see if, giving this freedom, we can alleviate the two tensions at a time. We have done that by studying this parameterization, EDP, which is very, very, very simple. So it takes the dark energy density takes this very simple form where ρ1, ρ2, ρ3 are constant, and W controls the dynamics in the late-time universe. Okay, ρ3 though can be computed also from the value of H0, omega CDM, and omega V, basically. So it is not a free parameter in the field. The corresponding pressure can be computed very easily because we consider that this dark energy fluid is self-conserved. The fraction of ED in the radiation-dominated epoch and in the matter-dominated epoch, that is the size of the two plateaus in the fraction of early dark energy, can be computed very, very easily using these dimensionless parameters that I defined here. Okay, so in this EDP parameterization, you find something like this with two plateaus, one in the matter-dominated epoch, another one in the radiation-dominated epoch. They can be different. We have also explored what happens if we switch off ED in the radiation-dominated epoch, and also if we switch on ED at some point in the matter-dominated epoch. For instance, in this case, we switch on ED at redshift 100. Okay, this is the two parameterizations that are particular cases of the original one. So just to mention, I will not provide details here, but it is possible to study this, to formulate the scalar field analog by using two exponential potentials. Okay, but I will not stop here. So which are the data sets that we have employed in this analysis? We have used temperature, polarization, and CMB lensing data from Planck 2018. We have used the Pantheon compilation of supernovae of type 1a. We have used the shows prior, not on H0, but on the absolute magnitude of supernovae, which is measured in the first steps of the cosmic distance ladder. Then we have used also BAO and redshift space distortions data from various galaxy surveys, and we have used this prior on S8 from wave lensing data provided by KITS and the dark energy survey. Okay, strictly speaking, this can only be used for the lambda CDM, but we have introduced this prior just to explore what happens, what is the impact of in the sigma 8 tension of our models. Okay, so these are the fitting results that we obtain by using just temperature and polarization CMB data and supernovae. Using the ADP parameterization, you can see that we obtain very, very, very strong constraints on omega RD and omega MD. They have to be below 2% and 0.7% at 2 sigma confidence level. These are the 2 sigma constraints, and these are the 1 sigma constraints. You can see that the tensions are not alleviated at all or very negligibly. And and another thing that I would like to mention is that by switching off the ED in the radiation-dominated epoch, we obtain constraints which are basically the same in the matter-dominated epoch for omega ED. Okay, so this means that the two constraints are almost independent. Actually, the correlation coefficient between these two parameters is only of 6%. Okay, what happens if we include the CMB lensing and the absolute magnitude, the prior and the absolute magnitude of supernovae of type 1a? Then, of course, we force the value of H0 to increase. Okay, we find a very similar problem to what is found by Poulan et al. So we obtain values of omega CDM which are much larger, values of sigma 8 that are also larger. But notice that the values of the upper bounds on omega RD and omega MD are basically, or are very close to the ones we obtained without including the prior on M. So this means that all the effect, all the alleviation of H0 comes in this case from this phantom value of W, okay, which is now 3 sigma in the phantom regime. What happens if we switch on the early dark energy at some redshift in the matter-dominated epoch? So you can see that when we switch on it at lower redshifts, then we
3 minutes, Adrian.
yeah, we include yeah, thanks. We get weaker constraints, but when we also take into account BAO and redshift space distortions, these constraints are below 1.4%. So we get a very stringent constraints. So this again shows that the sigma 8 and H0 tensions cannot be alleviated. When we include redshift space distortions, data on redshift space distortions, the value of W has to be very close to -1 in order to keep under control the value of sigma 8. So we cannot have phantom values, basically. This is aligned with results obtained in previous works. We obtain also weaker constraints when we lower down the value of the sound speed of early dark energy. Why? Because then we obtain basically a full degeneracy between the cold dark matter and ED. Okay, if we set CS squared equal to 0, then the constraints have to be exactly the same, because we have the same fluid basically. Okay. So okay, so we have explored what happens if we are more flexible and we allow for other shapes of the fraction of early dark energy. And what we have done is to bin the dark energy density in the late time universe, in the matter-dominated epoch, and in the radiation-dominated era. We have used 11 bins, and these are the results that we obtain for the reconstructed shape of omega dark energy. The left column does not include the CMB lensing, and the right column includes the CMB lensing. Okay, but the results are very similar. So let us focus on the right on the case in which we include the CMB lensing. So one thing that I would like to highlight here is that we are able to constrain a lot the amount of early dark energy around the decoupling time. This is why we obtain this kind of minimum in all the reconstructed shapes, regardless of the data set under consideration. Okay, so we obtain an upper bound of 0.7% more or less at 2 sigma confidence level between redshift equal to 1000 and 2000. Okay, when the prior on M is not included, then we obtain an upper bound of 3% more or less. But when we include the prior on M, then the fraction of ED in the radiation-dominated epoch has to grow in order to loosen the H0 tension or the M tension, and reaches 4% level. Okay, there is a 2 sigma evidence, let's say, in favor of the existence of this ED in the radiation-dominated epoch. But it, of course, worsens the sigma 8-1, as happens as was reported by Poulan et al., for instance. Okay, so let me show you that when we include the prior on M and the prior on S8, the H0 tension stays at 2.13 sigma. Okay. But it's curious because if we analyze the tension not in terms of H0 but in terms of M, we obtain 1 sigma more of tension. So ED has some difficulties, but this difficult. So Poulan et al. Say that you can loosen the H0 tension, but when you formulate it in terms of M, the alleviation is not as high as one could think. So yeah, so I just wanted to mention that. And regarding the values of sigma 12, thanks to the inclusion of ED in the matter-dominated epoch, you can keep the value of sigma 12 S12 quite under control. Notice this is interesting, and also is in connection with Ariel's talk. Sigma 8 and S12 do not coincide. Of course, this was expected because the effective scale at which you are computing this root mean square fluctuation changes. And as these models favor larger values of H0, sigma 12 tends to be lower, okay? But nevertheless, this tension stays there if you do not include the wave lengthening prior. And this is, I just read the conclusions and I finish here. So we have obtained very tight upper bounds on the E diffraction in the radiation and matter dominated epochs in the context of dark energy models with scaling solutions. We have seen that they do not alleviate significantly the cosmological tensions. We have performed a model-independent reconstruction of the fraction of early dark energy, still assuming CS squared equal to 1. We find very strong constraints around the CMB decoupling time. Okay, and large values of the fraction of ED in the radiation-dominated epoch allow larger values of H0, as it was pointed out in previous works in the literature, but typically lead to a worsening of the large-scale structure tension, which can be alleviated, at least partially, with a greater E diffraction in the matter-dominated epoch. We have also studied, I have not provided too many details about that, but we have studied this, how the tensions, which is the status of the tensions when you formulate it in terms of M and S12, and more details will be found in the paper, of course. And that's it. Thanks a lot.
Thank you very much, Adrian. Is there any question on this talk? Adria, I'm confused in the number of parameters that you use. I mean, because you are not improving. Well, this is one question. The second is, since you used more parameters than usual, I guess, I suspect, then of course the question is about the information criteria. So let's start with the number of parameters, right?
Okay.
Because, for example, the dark energy has several components, different rows, row 1, row 2, row something, and then you also use a potential. And please, could clarify this?
We have, in principle, if you look at the expression of the dark energy density, you have 4 additional parameters with respect to the lambda CDM, let's say row 1, row 2, row 3, and the late time. So the question of a state parameter in the late time universe for dark energy, okay? But actually we have 3 only. Because why? Because row 3 or any of the other 3 rows here can be fixed if you know H0, omega CDM, and omega for the baryons, the baryonic energy density. So one of these 3 rows is fixed if you are varying in the fitting in the Monte Carlo analysis on H0, omega CDM, and omega B. So in practice, we have 3 additional parameters with respect to the lambda CDM. But what I wanted to mention is that here we have not focused on the information criteria. We just wanted to know up to what extent could a combination of early dark energy in the pre and post recombination epochs loosen the H0 tensions, independently of the number of degrees of freedom that you introduce. Because, for instance, in the bint analysis, we have considered 11 additional parameters, 1 for each bint. Even in this case, we are not able to loosen at least completely the tensions, okay? But it is interesting to observe that we are able to put very tight constraints on the amount of early dark energy around the decoupling time. And this is done in a kind of model-independent way. Of course, it's not completely model-independent because we are assuming a Friedmann-Lemaitre-Russell-Walker metric, we are assuming the flatness of the universe, we are assuming that the sound speed is equal to 1. So it's not completely model-independent, but it's more model-independent than if you just assume one parameterization like this EDP. Okay, so yeah, so if I can tell you that if you consider the number of degrees of freedom and you penalize them using a Bayesian information criteria, then this model would be excluded. Okay, but yeah, this is not. But this was not the main aim of the paper. The main aim was to put constraints, let's say, independently of the number of beams that you consider.
But apart from that, I mean, why do you suspect that that there must be a component of the dark energy which evolves so fast as 1 plus z to the 4th, 1 plus z to the 3?
Okay, yeah. So this is just because we were inspired by these quintessence models with scaling solutions. This means that as it happens, for instance, with this quintessence with an exponential potential, you obtain two plateaus in the ED fraction. One in the matter-dominated epoch and another one in the radiation-dominated epoch, okay? So in order to generate these plateaus with our ED density, with our parametrization of the ED density, then you have to assume that it evolves like this, rho 1 multiplied by 1 plus z to the 4, because this is the term that will generate a plateau in the radiation-dominated epoch. These two terms will be negligible, and this term will evolve as radiation. So when you compute the ratio of rho dark energy divided by rho critical, which is basically rho radiation, then it will be just a constant, which is rho 1 divided by rho 1 plus the current radiation energy density. And then the same happens in the matter-dominated epoch. In the matter-dominated epoch, this term is negligible, this term is negligible, and this is the term that dominates. So this is a very simple parametrization that allows us to generate two plateaus, which are independent, can be fitted independently.
I understand.
Yeah.
Any other question? I have a last question concerning the potential, because you introduced the potential, but you didn't use it anymore, or maybe I lost something.
Yeah, because I went too fast, maybe.
Okay.
Let me.
Because these are two analyses, one with the potential and the other without it.
We introduced this just in an appendix of our paper, let's say, because what I mentioned here is that we could have also explored these two plateaus model, not using a fluid parametrization, but using two potentials with a scalar field. But this is of course more complicated at the technical level if you want to implement it in a Einstein-Boltzmann code as class, for instance, and it does not add more physics into the problem. So the main physics are already contained here. So we do not gain a lot by doing that.
Thank you very much. Okay, so if there is no more questions, thanks a lot, Adrià. I cannot see Ed Macaulay in the list. If he is there, please say hello. I cannot see him. So this means that we have finished. So I would like to thank all of you because everybody did a very good job, and within time. There was some shift or overall shift of time, but this was because in between different speakers, of course, there was some delay, but everyone restricted within the allocated time. So thanks a lot for the effort you did. Since there is some time left, if somebody wants to ask a question to the previous speakers, if the speakers are there, they can use this time or part of it. Up to you. If it is not so, of course, I will close the session. But at the moment, I want to give you this opportunity to ask more questions to the speakers, whichever you want. Okay. So So if it is not so, thanks a lot to all of you. And if you want to follow the CM3 sessions, the next one will be on Wednesday at 9:30, okay? So I hope to see you all there. So see you on Wednesday. Thanks a lot.
Thanks.
You.
Bye.
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 Bye. Bye.
Bye.